Good morning. If you could please be seated, we can get it started. Good morning again. My name is Atam Dhawan. I'm Interim Provost and Senior Executive Vice President. Also, I'm Senior Vice Provost for Research and the Executive Director of this particular program that's called Undergraduate Research and Innovation. So welcome. Welcome back to those who joined us yesterday. This is the day 2 of the Undergraduate Research and Innovation Summer Symposium. Yesterday, there were about 150 plus students over here, and about 80 students presented. So today, the rest of the students will be presenting. Also, today is a very special day. It is the National Academy of Inventors NJIT Chapter Innovation Day. And we named this particular Innovation Day after one of the co-founder of the Interdisciplinary Design Studio. He was with me when we started this particular program in 2012. And the program that time was called Interdisciplinary Design Studio. And he was with the board and a very, very big supporter, and not only a very enthusiastic funder. He supported financially, but also he mentored the student. He promoted the undergraduate research, innovation, and entrepreneurship, and inspired students by providing the competitive awards. And we started around 2014, 2015, the Innovation Day. Sadly, he passed away during the pandemic, but he wanted for us to create a stable and sustainable pathways for undergraduate research, innovation, and entrepreneurship. So we integrated the Innovation Day with the Undergraduate Research and Innovation Symposium and the National Academy of Inventors chapter at NJIT in his memory. And today, the board will be selecting from the student presentations yesterday and today the 8 best projects. 3 of them would be presented: the first prize, second prize, and third prize. The first prize is $1,000, the second prize is $750, and the third prize is $500, along with 5 honorable mentions of $100 each in each of the cluster area. They are all the part of Dr. James Stevenson Innovation Award, and they will be presented a trophy and certificate. This is a great recognition of our students, their accomplishment, and their dedication to the research and innovation. Yesterday's presentations were marvelous. The board was blown away. They told me they have the hardest time in figuring it out today who are going to be the awardee. So I'm sure that today's presentation will set the same tone for the board. We want to have the board a challenge to select the awardee. At the same time, I would like to express my deep gratitude to the board members for their continued support to this particular program since 2011-12, when we started the program as Interdisciplinary Designer Studio, and then around 2015, we turned it around and named it as Undergraduate Research and Innovation. They have supported this program with the tremendous financial support, but also their time that they have devoted in reviewing the proposals, mentoring the students, and also judging the summer research presentations. So thank you so much. Give them a big round of applause. At this time, it's my great pleasure to request our 9th president, Dr. Tech Lim, to come to the podium, give some welcome remark, and also introduce the keynote session.
Good morning. Thank you, Atam, for allowing me a few minutes to speak this morning. I was thinking about his remarks, having the judges judge the competition. And two things come into my mind. One is, hopefully, you'll take it as a joke. I hope you're not grading me and Tom and our speakers against the students, right? Hopefully not, because they'll probably beat us because our students are really, really good. No one laughed? It was a joke. Second thing, okay? Second thing is serious one. Serious, okay? The undergraduate research events here and also activity and program here, I think, since I've been to many states, okay, and many institutions, it's one of the finest in the nation. And believe it or not, even those students who don't participate in undergraduate research, they feel, okay, the success of this program and things that are going on because they talk to their friends say, hey, I'm doing this undergraduate research, oh, that's neat, and what are you working on? That all, okay, leads to, in a very simplistic manner, I want to put it, happy student. And happy student leads to happy grades. And happy grades, guess what, leads to excellent graduation rates. And this is one of the reasons why, even though we're a public polytechnic institution, all our degrees are tough degrees, right, students? They're not easy degrees. Calculus, physics, chemistry. I won't even remember my calculus now, sadly to say, even though I'm a mechanical engineer. In fact, last week, some of our board members and I toured the pre-college program, and they were doing calculus. And when I look at the problem and say, well, maybe I need to think twice whether I was able to solve that problem, given that it's been 40 years ago. But my point of the story, okay, is that this program leads to student success on this campus. And student success is what drives the reputation and the ranking of this institution. We're ranked top 50 among all public institutions in the country, top 100 among all public and private institutions in the country. And we all know size matters in ranking. Even though we're small but mighty. So I want to thank the students for contributing to our success here and our reputation. All right. With that, okay, I wanted to introduce one person for students who don't know. I know many faculty and visitors here know him well. Our first keynote speaker, a very special individual because he's both a leader of NJIT, a researcher himself. Mr. Robert Cohen, he was going to come out in a moment, but I want to introduce him first. Robert is actually the chair of the NJIT Board of Trustees. The Board of Trustees has a fiduciary responsibility to be the governing board and the caretaker of this institution. Effectively, they are my boss. Number two, he's also a 3-time NJIT alumni. 3-time, okay? I think that's a record. I don't think anyone got a 4-time NJIT alumni. Thirdly, he's very successful in his career. He's a president of Stryker Digital Robotics and Enabling Technology. Robert, I hope you don't mind me saying that students who are interested in that area, wants a job, talk to him. Among his many distinctions, he holds, think about it, he holds 25 patents. I don't think many of our faculty hold 25 patents. He holds 25 patents. And so he's an inventor himself. He's a fellow of the American Institute of Medical and Biological Engineering. Fellow is typically the highest status that you can achieve in any professional organization. He is a board member of the R&D Council of New Jersey, so he engaged with other researchers in the state. And last but not the least, he's also a Stryker R&D fellow. With that, I want to welcome Robert, and pay attention, he's got really great things to share with you. Robert?
Thank you, everyone. 1, 2, 3, got it? Okay, I'm not standing behind a podium. Okay, so, you know, right? It's 90 degrees, you're sitting in a ballroom in a student center at the end of July and you're trying to figure out why you're not at the Jersey Shore. I get it. So maybe I could share with you some things that I think would be interesting. The other things, just to clarify a few things, right? The longer the description of you get before you get on a podium just means you're old, and it's just longer you go. The second thing, just to clarify, Tech said it kind of effectively. No, I am Tech's boss, by the way, so just so we know. So the food here could do a little better, Tech. That's all I'm saying. So thanks for being part of this. Thanks for contributing. Thanks for the energy. Back when I was at NJIT, I will tell you, this same event catapulted my career. At the time, it was Sharing Plow, and Sharing Plow offered something exactly like this at NJIT. The big difference was my prize for winning was $100. So good thing inflation gets you up to $1,000 and more. So, but I will tell you, when I put that on my CV and resume, you know what attention that got for jobs? I actually got more job offers when I graduated this university, and it was a long time ago, because of the recognition, and not just because you got an award, because I participated with it. I could tell you right now, there are 160 total NJIT alum that work at Stryker throughout different divisions. Up in Mahwah, New Jersey, there's about 120 of them. And by the way, Stryker's a big company. In fact, just to give you an idea, technology company on this doesn't work. Is it moving? See now. There you go. Oop. Tricky one, huh? Okay, that's Stryker. So by the way, at Stryker, we get Harvard, we get MIT, we get UCLA, we get Stanford, we get University of Miami. We get lots of different schools, but I'll tell you what, there's a preference to NJIT, not because alum and we're favoring NJIT. NJIT and NJIT students, the research you're doing is so compelling. You actually, when we hire you, you actually create a jump start. You don't need 1 or 2 years to get acclimated or onboarded. There's a contribution that's amazing. So let me give you a little bit of my perspective. I will start off by telling you, I am very humbled. I am very fortunate to have been in med tech for 35 years. I've had the opportunity to invent devices that have touched millions of people. I've also had the opportunity to head up groups that have touched hundreds of millions of people. Think about that. When you graduate from here and you get to do that, the personal satisfaction you get out of one of your designs, one of your inventions, that actually goes in a human body and gives that person a quality of life that they wouldn't have had otherwise. It really is truly remarkable. So let me give you why you want my job. You should want my job. I want my job. I still get excited about doing what I'm doing. Okay, for those of you at Stryker, if any of you broke a bone, any of you had to go to a hospital, any of you had to go to an emergency room, you probably saw a Stryker bed. If any of you had to go from that emergency room up to a patient room, you chair. If any of you were in back of an ambulance, 70% back in an ambulance. Is this thing working or what? Yeah, right. You guys good? Okay. No, the guys in the back. I get fussy about video and stuff like that. You figure people got long enough time to set this up. These things should work right. So now, when you think about that and you think about the patient room, think about being in a patient room. But then think about the operating room. Do you know Stryker is the only company that can outfit 100% of an operating room? Do you know, you probably know someone, a grandmother, grandfather, aunt, uncle, who had a total hip or a total knee? There's a good chance 1 out of every 3 in the United States implanted is a Stryker hip or knee product. Shoulder, trauma, spine, sports medicine, ACL fractures, all of that. But it's a big, complicated company, $20 billion in sales a year. It's a Fortune 250 company. It's one of the largest, most successful 80-year history. But I'll also tell you, for you, if you're interested in med tech, it is the most exciting time. And by the way, whether you want to be robotics, machine intelligence, whether you want to be data science, whether you want to be cybersecurity, mechanical engineering, electrical engineering, robotics, materials, it's all part of what Stryker needs to do. You put something in your body, it's not just a hunk of metal. Someone had to design it, someone had to put it in the right place in someone had to make sure it was going to last a lifetime, someone had to make sure your body wouldn't reject it. Think about that. Think about that responsibility that you have. But I can tell you right now, there's a convergence of technology, and you are so fortunate. And the reason you're fortunate, when I was back in school here, it's like, okay, we created a new alloy. Great, now make some materials and out of a new alloy. Now, you got the convergence of technologies. You got robotics, you got AI, you got different materials, you got design capabilities, finite element analysis. You could do simulations that we never could have done before. You could design something virtually before it's even made and having a high level of confidence that it is truly gonna work. So exciting times. Let me give you an example. I am in med tech. Most of you, I'm hoping, want to be in med tech. So I'm going to show you some pictures, and it's part of the human body. It's part of what we do. So firstly, get used to it. It's what I do. And it's all for the purpose of making people feel better. So if you're queasy or anything, I apologize, but you know, it's design, and design's got to work in conjunction with human body. See this? It's X-ray. You know what that X-ray is of? Does that look right? Someone got in a car accident, and someone had a knee implant in them. And guess what? Their knee went into the steering wheel, and it crushed their bone. How do you fix that? You got to get someone's leg aligned right. You got to put in another implant. So look at what we do. This is a difficult design, right? You know what? This is mechanical engineering. It's mechanical engineering. Here's the bone that's left. Look at the void. The guy from heads up like entrepreneur stuff is queasy. Look at that, NJIT faculty. Jeez, go. So look at that. That's a void. How do you make something structural to put the implant in it, right? Okay, because really what you want to do is you want to put something in there that can hold up an implant. So we put a cone inside the bone to get the joint line back. All right, let me show you how you design that nowadays. Now, finite element analysis, I have the capability to take 3,000 CT scans, 3,000 CT scans in 30 minutes. And I could simulate surgery on 3,000 people on a computer. And then I could design, I could invent, and I could try different shapes. And I could optimize shapes now all virtually, all with computer science. And then after that, I could come up with these configurations that are awesome. But you know these configurations? Okay, well, I just made a great configuration. How do you make it? Manufacturing engineer, quality engineering. How do you make it? Well, with the advent of 3D printing, now you could make virtually any shape. You don't have to worry about conventional manufacturing processes like mills or lathes or something like that. So now what you do is you take that, and now I can make that shape, and I could 3D print it. And look at that. I got solid metal on the inside, porous metal on the outside, so bone can grow into. So let me give you an idea. This is actually our Stryker facility in Ireland. This facility is the largest, repeat, the largest 3D printing medical med tech facility in the world for structural metals. If I showed you, and you pull up to the front of this building, is a fascinating building. I can tell you we leave it, and we leave it secure as a completely separate building because of all the trade secrets we've been able to do, inventions you want to keep, and you don't want to tell someone necessarily how you make it. And if you open up and you look inside, these are all 3D printers. And you know what? They don't know what a holiday's like. They don't know what a weekend's like. They operate 24/7. You don't see a lot of people there. You know why? Because in my Mahwah, New Jersey office, just 45 minutes north of here, we have people doing the programming. It's sent directly to the machines. See those machines with the green lights on? Those are machines that are actually working. And you just need people once a day. They come and they look at what was made, and they reload, and they put new materials in it, and then send different programs. It's totally automated. It's totally computer science. STL files, things like that, you just send directly to it, and you get what you make. So if you're not familiar as much with this is what I'm going to show you. If you looked in the window of one of those pieces of equipment, that's what you're going to look at. That is a powder bed. So think of just like a little sink. It's filled with metal powder. But powder, really fine powder, 50 micron powder, like baby powder. If you toss it up in the air, it creates a fog. That's how fine it is. It's titanium. So we use titanium. Why? It's biocompatible. It's inert material. So now what we do is we take our program, and we run the laser, layer by layer by layer. The program tells the laser where to go. Anywhere the laser touches, it consolidates the powder, and the powder becomes a solid. And then we just keep doing. This is making acetabular cups, hip and knee sockets in your hip. So this is the socket part. This is the face of the socket. I'll show you what it's like. But that's a laser, and we're doing the inside, the porous, all with no manual machining. It's all just done fully by programming. And then after this is done, after about 20 hours, like an archaeological dig, you move around the powder that the laser didn't touch, and look what you uncover under it. So think about from the world of invention. I've been able to come up with different inventions just by now looking at different manufacturing processes that enabled my mind to think differently. So super exciting. And as you move these around, here, look at what was created. And all we do, those little round solid holes, that's for bone screws to help secure for fixation. And look at the configuration of the material. Here's what it looks like. So that's a hip socket. Look at that. It produced it on 3D printing. And it produced it in 20 hours. Normally for a prototype 20 years ago, it would take me about 3 months to get someone to make something like that for me, and they couldn't make that porous material. I can actually do iterations of prototypes and designs faster than I ever could before. That's good. That's good for a public company. More revenue, more time to market, more patience that you impact in a better way. But look at the detail. We actually designed in the friction of the outside when it goes against bone. So we actually engineered unsolid models of friction, and the 3D printer is able to do it. And now look, long term, you want bone to grow into it. So we've created this structure surface that, look at the pores. This is actually bone will grow into it. We actually trick the bone to think it's bone, and bone grows into it. So through 3D printing with models and configurations, we've done well, right? Okay, what's the next thing we need to tackle? Big problems. Sadly, everything we do isn't just for hips and knees and getting you back up and going. We handle oncology, tumors in bone, big accidents, big fractures. We're actually doing a lot on war injury right now. And we're helping out war injury and people with landmines, which is a disgusting thing that still happens all over the world. And you need to restore people's bones. This is 3D printing. You see in the upper right, we recently did this as a total pelvis for someone. Someone would have been stuck in a wheelchair for their whole life. We were able to give someone the gift back of being able to walk. Think about that as an inventor. Think about that as an engineer. You've impacted a person's life in ways that they can't be thankful enough about. Okay, now, I showed you we could design an implant differently. I showed you we could produce an implant differently. We got another problem, right? Look at this. Implant placement. Every single person in here is different. Every single person's knee in here is in a different place. Everybody's joint line, everybody's flexion, you are all different. There's no two people inside that are alike. And if we take then a look at alignment, look at this. This is a partial knee. It failed because the knee's in the wrong spot. If you look at hips, you know how many people are walking around with 1 inch longer leg after total hip surgery? Because the metal was put in the wrong spot. Center of rotation in the wrong spot. You know how many people can't walk up and down stairs, right? And look at this knee alignment. This is a 3-dimensional problem. Women have different placements of where their hip needs to be in angles. Men have different cultures, different regions around the world. It's very, very different. So it really is quite remarkable when you think about it. Okay, so we're all friends in here. We design a good implant. I design a good implant. You want to reduce variables. You want to limit problems. Where's the next biggest variable after I design a big implant? Shout it out if you can think about it. OR? Who's in the OR? Yeah, surgeon, human error. And you know, the reality of it is, there's kind of a joke. There's no surgeons in here, is there? Mark's laughing. Okay, one of the jokes is if you have a graduating class of 1,000 people who graduate medical school, what do you call the 1,000th person with the lowest GPA but graduated? Doctor, that's right. And why do people go to hospitals for special surgery, Mayo Clinic and Cleveland Clinic, versus maybe a local hospital? There's different skill sets. It's just human. It's not their fault. But the same goes for a lot of industries. If you want to take a plane to London or India, I know some people from Calcutta, you want to fly from JFK Airport to Calcutta. You prefer the pilot flies the plane the whole way, or you prefer autopilot? You know you prefer autopilot. And what's this all about? Getting from A to B, right? So why is an implant any different? So welcome to the world of robotics in the operating room. And that's to reduce. It's robotic-assisted surgery. Surgeon is still the surgeon. This is to get to the target. So that's a robot. That robot is here to stay. There's never been a robot that entered an industry and left it. There's never been a robot that entered an industry and that industry did not benefit from it. And MedTech will be the exact same. I've been very fortunate to be able to work on this robotic system for 15 years now. And inventions are very different. You know, inventions, you used to think of embodiment of a piece of metal or plastic in your hand. Now inventions are robotics, electromechanical machines. Inventions are software and applications that you put on this robot. So that's a robot. See the saw on the end? The purpose is to get that knee. If it's you, CT scan of you, individually we figure out where that goes, we load it in the robot. Here's an example. This is a saw on the end of the robot, right? Look at the saw. We can hold the plane of the saw exactly to cut the knee where you specifically need it. And because I'm Stryker, I can actually get saw blades, power instruments, things done in amazing ways. This is the way you start. CT scan of you, your actual bone. This is not a cartoon. This is a representation of an actual patient. And this patient, the green, is the benefit of a Stryker knee. So this is the prosthetic part to cover the arthritis part in the joints. But look how virtually 6 degrees of freedom. Now you're untethered. You can move it anywhere. Individualized medicine, getting it exactly where somebody needs it. Okay, then you lock in the plan. And now this is intraoperative. This is before you do any cuts. We have the surgeon see what a virtual surgery looks like on the operating room table before they cut that patient's bone. So we can confirm where that knee is going. And then after we confirm it and all their ligaments are right, now the robot goes to work. And the robot cuts the plane exactly where the green is the bone that needs to be removed. And it cuts it with an accuracy that's up to about a 2,000th of an inch. It really is remarkable. And we could do much, much great things with it. Okay, so think about that. Now, let's go one step further. Okay. Anyone watches the news lately, right? Data, data science, digital, artificial intelligence, machine learning, predictive analytics, cybersecurity, product security, connectivity, right? Cloud computing. It's the rage. Well, guess what? A robot's a very digital machine, isn't it? And it's actually run with data. Now let's think about healthcare data. So by the way, it's not just, if you're starting a company, 90% of the medtech companies that started this, inventors, this is important, 90% of the funding of small companies last year went into AI medtech companies. 90% went into medtech companies. Isn't that fascinating? But also industry reports, when they look at reports, everything's now wearables. What's going on with your iPhone? What's going on with your Garmin watch? What's going on with sensors eventually you could put in clothing? And then, hey, we're a big company though. How does a big company deal? This is my job. So I represent this brand new division we started 2 years ago called Digital Robotics Enabling Technology. All of those gold boxes, those are all different Stryker divisions: neurovascular, stroke, medical, hospital beds, hip and knee replacements, endoscopy, laparoscopic procedures, interbody fusion spine, scoliosis cases, car accidents, trauma. Now, I pull all the technology from there: digital, metal, 3D printing, data science, and actually look at how to push it faster across all of Stryker in the biggest kind of way. And why do you need to do that? Well, if you need a surgery, and I don't know, did anyone break an ACL here? Anyone break an ACL? Really? No soccer players? Lacrosse players? You broke an ACL? Do you know anyone? Actually, in females soccer is one of the biggest now ACL growing aspects of it, just because cleats are so good and artificial turf is so good. People twist in a little different way and their foot doesn't move with them, so they pop an ACL. And the other people who are popping ACL is a brand new market for us. And keep in mind, we love ACL poppings. We make a lot of money on that. You know what's great for people in their 60s and 70s, and you got Brian here and probably plays and shouldn't? Pickleball. So all these people thinking they're getting healthy with pickleball shouldn't be playing pickleball. It's really not like table tennis. It actually becomes more competitive, and you get people in their 60s using ACLs, and they're twisting, and Brian's going to be a patient one day, so we're looking forward to that. And Brian, you got 2 knees to give, so you got 2 knees to give. No, you won't. We'll fix you before you die. 2 knees to give, and we appreciate that. But now look, if you had an ACL reconstruction, you no longer want to be in the hospital. You know how you do that? One-day surgery. You know how you do that with safety? STEM, engineers, data science. We're the ones that design it. We design the procedures. We design the instruments. So this is now everybody wants faster, faster, faster. Nobody wants to be in a hospital anymore. It's not, does my implant going to last 50 years? I want to feel good in 2 weeks. I don't want to go to physical therapy. I need to go back to work. I'm paying too much deductible on my insurance. What do I do? Engineers are hospital efficiency. That's us. New implants. That's us. New ways of working, doing the procedure differently, that's us. New instruments to execute the procedure, that's us. Even down to the instrument trays that carry the instruments to sterilize them, that is us. That is all inventions that happen in the technical world. And I'm pretty fortunate because Stryker already has these products, everything from back of an ambulance, power instruments, they're all capable of capturing digital data, right? And I'm going to start sending it to the cloud. And for those of you interested in cloud, computer science, or whatever, I have a cloud that takes data from 65,000 patients a month. Identifiable data that needs to be secure. 65,000, think about it. I have more data than anyone else has. And you say, well, what kind of data? What kind of data are you looking at? So I won't bore you with this, but you may think, I'll just use a total knee example because it's easy to think of a knee replacement. I can actually look now at the time of the procedure. I can look at how quick the surgeon is. I can look at what the surgeon does in a session file from the start to the end of the case and replicate the case digitally. I can look and port out the final three-dimensional placement of the implant. We never could do that before. And that's a digital asset that now could contribute in many different ways. So you say, well, what's the difference? Here's the difference. I could tell you what Stryker implant now is best for you based on your body condition. I can also tell you where the implant should be based on statistics and population health. I can also tell a hospital for operating room scheduling how long that surgeon takes to do a procedure and how many procedures a day you can get out of that operating room. I can also now look at complication rates, readmissions, reoperations. Unbelievable, and that's Stryker. And that's the world of technical doing that. There's nobody else doing it. Now you combine all that data, it really is fascinating. So what do you do with it? This is the real deal stuff. This is a real patient. See this patient on the left? Or this is the same patient. This is the left, on the left knee. This is a simulation of their good non-arthritic joint and replicates their motion of their non-arthritic joint. Well, why not have the knee replacement on arthritic be as good as their normal healthy knee? So now we superimpose on their arthritic knee a solid model of a Stryker implant that replicates the motion exactly. We only started to be able to do that about 1.5 years ago. But that's all due to this digital data we were able to get. Now, how about this? This is all damage from arthritis. We now, with artificial intelligence, can pre-map what bone is real versus what bone just grew from arthritis that needs to be removed. And we can now show with colors the surgeon what bone that needs to be removed. Additionally, we're working on iOS mobile apps. So we now have iOS mobile application engineers that just take things to an iPad or take things to an Apple phone in really remarkable ways. So we're giving the surgeon more information. And then what about HoloLens? What about Magic Leap? What about mixed reality, virtual reality, augmented reality, all cool stuff? Well, that digital data is an asset, and we could convert those models. We have this right now. My group just released this 6 months ago. Super excited, first time getting through the FDA. And now surgeon could wear these glasses. Look how we superimpose the CT and the plan right above the patient. The surgeon can actually see how accurate they are. The surgeon does not have to take their eye off the wound to look at a 2D monitor that's sitting. That's an invention, to be able to use it. So just using mixed reality glasses, that's not an invention. That's just a tool. It's what we do creatively that uses a tool that improves and impacts patients' lives. And I'll show you this just because it's cool. You may not fully appreciate it, but you may hear people get osteoporotic as they get older, especially women in their 60s and 70s. They wind up taking bisphosphonates, Fosamax, things like that. That's to increase their bone density. Now we've been able to actually take off the CT scan and look at where the implant goes and measure the bone density to understand the risk of this patient and having an implant loosening. And now we're providing this information to the patient. And then I said, everybody's different. How about alignment? Now we're automating with AI alignment of someone's leg to recreate what it should be. So remarkable innovations, and this is what a surgeon's going to see eventually. They'll be able just to, they get home one night, they're going to be able to just go on their iPhone, we're going to give them a secure login, they're going to be working off a Stryker cloud, they're going to see the plan, and these are all Apple screenshots of what we're putting, and again, data science in a big kind of way. So I will tell you though, what's most exciting though, is when we connect the world. There's different alignments of patients in China than there is in Japan, than Eastern European countries, than the United States, than certain areas have different disease states. And as we build this, we will build a population health library, and that's all STEM, and that's all technology, and that's all what we do. So I'll give you this, and this I just put in. So I just literally put this in because we just submitted patents on it. This is IP. You may not think of intellectual property like this, but now ChatGPT, OpenAI, all that kind of stuff, this is real. So what we did is I loaded in all 600 peer-reviewed literature on robotics, okay, for total knees. So now if you're a patient, you're home, and now you go to a Stryker webpage, and this is real time, by the way. It's like, hello, Mako, that's the name of the robot. Ask any question you want, any question you want. And through OpenAI on Azure Cloud, by the way, for those techie people, we have a patient, and this is a true thing. So this is real time. This is right off a prototype website we created. The patient put in, does a robotic knee reduce blood loss? I know in our world, watching this for 15 seconds seems like forever because people's attention spans, are instantaneous. But this is real time. And now this is real time going through OpenAI, through all the literature we have on the cloud, and it's actually coming up with an AI answer. And the answer is yes. Not only yes, it'll give the 3 most relevant papers. So it's not like a Google search where you're just searching for keywords. It's actually giving you a legitimate response. And then you can go forward again and ask any question. And we just had patients, hey, go ask any questions. And does the use of robotics, I know, waiting 5 seconds now. It's just like everything's so fast, right? Reduce post-operative. By the way, but this is inventions, and this is intellectual property. How we do this and how we string this together for AI is the real deal stuff. So I'll leave you with whatever you're thinking about doing, wherever your research, especially if you're in the world of med tech, all of these different areas play a role, but singularly, one by itself will not win enough. Singularly, if you want to improve the most, it's the combination of all these. It's a combination of an implant design to a person. It's a combination of what executes robotics. It's a combination of what digital health data can help you predict the patient's success rate and other comorbidities and other challenges that have. It's all these things combined that's going to elevate improved outcomes, safety, operating efficiency, quality of care, all things that are very meaningful. So thank you for listening. As you look forward, this is all automated in the cloud. Isn't it great? ACT scan in the cloud, automatic rendering. By the way, that's a rendering of a real patient. So look at the geometry and look at what you can actually see. Automatic implant placement and sizing, automatic simulation for what happens in flexion, automatically goes to the robot. It really is a great time. Congratulations for you picking a great industry. Congratulations to you all for the future. MedTech, as an example, is a exciting industry, but the combination of using all these technologies is just so remarkable for so many different things. Thanks for listening.
Thank you again, Robert. Your presentation, I'm sure, will have a profound impact on the research and the career of many of our undergraduate students here today. So let's have another round of applause for Chairman Robert Cohen. Our next speaker is a longtime dear friend and former colleague of mine from the University of Texas at Arlington, Dr. Deriji Agonafer. Among the many, many credentials and achievements of Deriji, the few that I will mention here, so that I'll give him more time to speak. He's a Presidential Distinguished Professor at UTA. I have the honor of bestowing him that honor when I was president of UTA previously. He's also the member of the National Academy of Engineering. For those students who don't know, most engineers will have a hard time getting the Nobel Prize. It's just the Nobel Prize is just cut it for engineers. But having attained National Academy of Engineering is like winning the Nobel Prize. He's also in the Academy of the Medicine, Engineering, and Science of Texas. This is the highest honor that the state of Texas bestow on faculty member and researcher in that state. And he's also an inventor. He's a fellow of the National Academy of Inventors. And one thing that some of you may or may not know, I think he's the most prolific advisor at UTA. Hundreds of students that have graduated, graduate students have graduated under him. So, Dr. Darajee, welcome.
Well, good morning. It's a little difficult to follow Robert. Outstanding seminar, really, really great. In fact, I wrote something on a card. I said that you were talking about ChatGPT, for example. Really, recently I read an article where Steve Jobs said, AI, what about AI? He predicted. It really is looking at things that you do and said, what can I do to make it better, sort of. And ChatGPT, from an invention point of view, going to open up a whole bunch of venues for young people. So really, you guys should certainly take advantage of it. So let me get started. First, I want to thank President Lim and his wife, Gina, First Lady. We had, what's that? Oh, I can see it there. Yeah, I see it. Okay. We had a great dinner last night, so thank you. Certainly, Tom Dewan, the provost, really gave an excellent seminar. So much so, excellent speech to us about what's going on at NJIT. I said, I may have to change my talk. Frankly, yes, absolutely. Yeah. Sure. Yeah, the reason I said I want to change was I'm a big believer in undergraduate research. Absolutely. So students might say, you know what, I don't have time. I'm taking physics, I'm taking calculus, and so on and so forth. Actually, when you do undergraduate research, what happens is engineering is applied science, right? So you come into engineering, freshman, and you start taking all this physics and math courses. The retention rate is really not that great. The reason is you don't get a chance to go into applied stuff early. So I really encourage you to knock on professor's door and say, you know, I want to do some research. In all the funding that I get, I put some funds for undergraduate research. For example, currently, this semester, in the summer, I have 3 undergraduate students, work-study, by the way, that are doing research in my immersion cooling lab. I have also 2 other undergraduate students absolutely believe in that. So I encourage you to do that. I don't want to hear this stuff about it's going to take away from studying. It would actually excite you because, gee, you know, if I can do this, you know, I see now how I can get an internship, for example. I see now how I can start bringing what Intel is doing, what Microsoft is doing, closer. And therefore, when I do get there, I'm ready to go. And so, yes. And Siobhan is a good friend. Thank you. Known each other not long, but it's been great. And Kim, thanks for all the information that you gave me. That was awesome, and I look forward to working with you. And I want the entire President's Board, great time. So, my personal background, early days, so I joined IBM, I left IBM in 1999, and I joined University of Texas at Arlington as a full professor. So some of you young assistant professors might not like that. That's a shortcut, but it was, you know, I got the opportunity. They kept encouraging me to come join academia, and I did, and I've had a lot of fun. I'll talk a little bit about, the provost had mentioned that we are very much into collaborative efforts. So I'll talk about one of the stuff that we have called IUCRC. And this is the third phase. We've got it for 2 years, two consecutive 5 years, and now we're in the third phase. CHIPS Act and heterogeneous integration. The CHIPS Act is something that happens once in a millennium. So all you young people, pay attention. It's a big, huge opportunity. You know, it's about $50 billion. $39 billion is for silicon, right? And the balance of about $11 billion is for packaging. So it used to be packaging was, you know, you make those transistors and you say, you know, I need to connect them to the board, so I'm just going to use wire bonds, or increase the area, I do flip chip and so on and so forth, somehow connected. And that's really very, very low money-wise. Not anymore. The reason is that the frequency between this silicon nodes, you know, you multiply by 7 every time. If you're 10 nanometers, then you multiply by 7.7, so you use 7 nanometers and so on and so forth, right? Double every year used to be, then 2 years. But the scale, the time between start increased significantly. In the meantime, what do you do for performance? You got to do something. So packaging is going to be big leverage, and I'll talk about that. Diversity is very important. I was recently in a panel on that. NAI, I'll quote a little bit a recent article. I was about a year ago that I was quoted on. And I actually really, really encourage, after hearing the provost talk about some of the stuff that you guys do for undergraduate research, that should be a model. It's absolutely, and I was just talking to Jamie about how that great opportunity it might be to really publicize what you guys are doing as a model. So importance of undergraduate research, NSF, the research experience, you guys got REUs. And there's also research experiences for veterans. I'll give examples of that. So, a PhD at Howard University. I joined IBM right after my PhD and did a lot. 15 years I worked there, absolutely beautiful. Didn't want to leave. Had nothing to do with academia, but I was recruited for 3 years. I wasn't, because I loved what I was doing. So finally I said, I'm going to try this thing called academia. Be honest with you, when I joined, I got a pretty good startup, but my first PhD vaulted on me, and I said, you know what, I don't want this guy with no experience and so on and so forth. So here it is, I had 2 PhDs, and one of them bolted on me. So it was a struggle, because I had a plan. My plan was to really bring some of the industry into academia, and it was successful. Like President Lim said, I've graduated 256 graduate students since I joined in 1999, and currently advising 15 PhDs, and we're having a blast. So I'll discuss that a little bit. So the NSF Industry University Cooperative Research Center, this is an effort by SUNY Binghamton, great friend of mine. Bagash Samaki and I have known each other, I don't know, for 30 years. Al Ortega have known each other for about 30 years as well. So good friends. So it makes it a lot easier to form a team. It's a really energy efficiency related to data centers. Data centers now are really a big thing. And so how do we make them energy efficient? So it used to be, you have this servers, you put them in a rack, and then you blow air in it. Absolutely not energy efficient. So we have done, I don't know how many, probably 150, 200 papers we published just in this particular area, and graduated many, many PhDs. I have 5 former students at Meta, Facebook, and several at Intel, and so on and so forth, doing this area. So it's an important area. And these are some of the companies that work with us. And we have bylaws and stuff. So now let me talk about the CHIPS Act and its opportunity of a millennium. I actually talked to when I had dinner with the board, the challenge was what's going on related to the CHIPS Act. It turns out that you guys are really doing a lot in the IRA. I think maybe a better opportunity, which is also several $100 billion, right? This is a great, great opportunity. It comes once in a lifetime. Essentially, what it is Gordon Moore recently passed away, so Intel posted something, and I reposted, that his seminal paper in 1965. I'm sure you guys have heard Gordon Moore. It's not really a law. It's just he proposed something. It was really he thinks that we can double the number of transistors every year. That's really what he said. And sure enough, in 1975. What he said turned out to be pretty true. But there was something more interesting. What I said when I posted this, reposted it, is Gordon Moore predicted the days of chiplets, heterogeneous integration, and his legacy continues forever. So let me stop here and talk about so if you look at nowadays system on a chip, right? System on a chip, you want to put everything on it. You want to put memory, logic, and so on and so forth, right? Just keep increasing it. But in the fab, there's a limit. It's called a reticle limit. So if you reach about, say, 800 millimeters squared, even though internally, some of my colleagues, not internally, it's always good to have friends. You can pick up the phone at Intel or others to chat and say, where is it? So maybe a little bigger, but there's a reticle limit. After that, the yield drops, the cost goes exponential. So what do you do? So what the big thing now is, and where $11 billion is allocated, it's called advanced packaging, is really heterogeneous integration. What that is you take these chiplets and you disaggregate them, right? You break it up into some functional units, and then you stitch them back together using different technologies. You may use a silicon interposer, 2.5D, or you may use Intel's EMIB technology to stitch things together. And it may work almost as good as the SoC. But now all that reticle limit you can throw away, right? Because you have small chiplets, and you can make them bigger and bigger. I have several thesis ideas on that. There's some limits, for example, how big can this, because somehow or another, you're going to have an interposer, so you're going to have some reliability issues. But it greatly increases reduces the cost by about 50%, and it's just a really, really great technology. So not only can you do it in 2.5D, you can also stack them 3D, right? And 3D stacking using through silicon vs and so on and so forth. So we have a few patents on how to cool 3D stuff. We actually got Thermoelectric, who's one of my former students, who was really doing well, but he said, you know what, I think I'm going to go into the banking business. He's a millionaire now, multi-millionaire in Singapore, and it hurts my feelings he left engineering to do that, but sometimes they do that. And this is when you know that packaging is going mainstream. So you heard what I said, is that it's not anymore about the next node, right? Technology node, right? Just multiply by 0.7, right? 0.7 squared being a half, right? You double the number of transistors. You can't do that, and also, only 3 companies now are in the 2 nanometer business. TSMC controlling 92% of the chips, and that's one of the issues. That's one of the reasons we're looking into putting some money in the silicon, and Samsung, and even Intel, but that's it. So what do we do? Packaging is a big opportunity. I was in a panel at Semicon West having a discussion recently, and Iyer was there as well. He's at UCLA, and one of the things he said, packaging is where the action is going to be. It's not anymore this interconnects, taking the wireframes or flip chipping it and, putting an underfill and so on and so forth. There's a lot more than that. It's how do you, there's architecture, there's mechanical, there's, thermal, and so great opportunity to look into it, right? So this was an article in the New York Times a couple of months ago, and of course, Commerce Secretary Gina Raimondo being very active on this. So it's a great thing to look into. It involves electrical engineering, mechanical engineering, and so on and so forth. So this is something very interesting to look at. And yeah, this was Semicon West. In fact, the person, when ITRS, International Technology Roadmap Semiconductor, when that ended, it was Bill Chen right here, a good friend of mine that started the HIRI, Heterogeneous Integration Roadmap. And she was from Intel, and so great people were there July 12th. And found out that I had to be at Purdue the next day, so I said to the conflict, you know what, I'm gonna cancel, but there's a lot of interesting things. I gave a keynote in Washington, D.C. on the 11th and 12th here, and so it's a very hot idea. The opportunity, some of the challenges are thermal challenges. TIM, it turns out that 40% of the thermal challenge, the thermal budget, is in the thermal interface materials. So there's a lot of opportunity for material science people, right? So what you do is, now you got the big silicon, you put a TIM on it. Now though, you got these chiplets. They might not even be the same size. How do you put the thermal interface material? Not trivial, guys. This is the problem. Thermal is a tremendous challenge, and thermal interface materials is very important. Heat sinks, fin efficiency. I know Robert talked about some of the FEM stuff, and chiplets. So whenever you see the word chiplets now, all you think about is disaggregation, right? You took the SOC and broke it up into pieces, and how do you get Humpty Dumpty back again, right? And make it perform almost as good, but at significantly lower cost. And reliability and hybrid bonding, and I have a couple of my students currently, PhD students at Tesla, interning. When they come back, this is what they're going to be working on. 3D stacking, immersion cooling. I saw on the board that there's some phase change folks there that I'll say a couple of things about that. So let me move, and there's some of the equipment. Equipments are really important. We just purchased this in my lab for about $600,000, nano indenter, and I want to thank President Lim for the funds he allocated before he left. Thank you. And this is some of the work that we're doing with it. This was the old indenter, and this is the new one. We have a couple of students, Jake and Joseph from Lockheed Martin, doing their PhD. And this is the new president visiting our lab, April 14th. So this heterogeneous integration, I was in Sweden, National Academy of Engineering and Royal Academy, June 20th or something like that, and we were talking about 6G. 6G is on the way, so by 2030, right, 6G will be up there. So we were talking about that, and the CTO, Malik, from Ericsson, and we have had lots of discussion. But are you anticipating now, how does 6G and heterogeneous integration play a role in the 6G? And that's really something I'm looking at right now. It's something very interesting. And we also there was an Intel Day. Good friend of mine, Dr. Ashish Gupta, we actually got funding from Intel. Currently, we've been working with them for the last couple of years, and it's on immersion cooling. And this was an Intel Day. Important to participate. Diversity panel, but this was at, how many of you go to a conference called ECTC? This was at ECTC and iTherm, and this was a panel we had diversifying our technical workforce. And again, on President Biden's remark on the CHIPS Act, and $39 billion to manufacturing. This is silicon, and this is R&D, right? Visions for success. You'll have most all of this slide, so I don't want to go into detail. Now, and here are, we're recruiting undergraduate students. Both of them are actually veterans. I mean, they served, he served 6 years, and he's also in the armed forces. So he is a U.S. Marine, and so they're doing an excellent job. Currently, this summer, they are working on a nuclear NRC-related project. We had to use U.S. citizens. So they're working with me, plugging away. And students do visit, they were in Houston looking at an immersion lab, and Ashley, she is, right there. She's actually a work-study student that is doing a great job. She's in our lab this summer, and as well as, So Allison Boyne, I invite speakers from industry. So one thing you guys can do in the engineering science courses, I don't care what people say, it's just, hey, God, we only got so many lectures. Invite speakers on a timely basis. For example, thermodynamics right now, right? There's a huge interest in alternative energy, right? Wind, so on and so forth. So invite speakers, right? And look at from industry. So I think the industrial base is really great here. And I started a certificate program in electronic packaging. When I say this class is full, as soon as the class goes out, it's about 100 people we have. Graduate students, about 20 slots for undergraduates. It fills up right away. So we talk about, except packaging is going through a renovation. So now I have to find ways to change the topic. And here is the program, Academic and Research Leadership Network. I encourage you guys, if you're looking for minority faculty, to look at this. Now, let me quickly, let me look at my time. How much time do I have?
We wanted to leave some Q&A period.
Yeah. Okay, let me talk about, I'll go very quickly. So this is degree of cooling difficulty. Basically, Moore's law was working just fine. There's a physics behind it called Dennard scaling. Dennard scaling is the power density scarce, right? Voltage times current divided by the area, so everything was one. But starting about 2004, Dennard scaling failed. When that failed, so when you go to places like to buy a computer at Best Buy and so on, you can only talk about frequency. No more frequency froze, so no more frequency. It's just cores. And so there's a lot of power was fixed, but now there's a power war. So because of that, so we're doing all kinds of stuff. This is direct evaporative heat exchangers. It's really swamp cooling, and I'll move on to that. And we actually built a data center, and guess what? We completely got rid of them, 450 servers, to bring in a $2 million liquid cooling lab. And this is some of the work that we're currently doing. Indirect, this is we're working with a company called Mestex. I'll move very fast here just to give you a taste of what we're doing. This is our immersion lab. Lots of companies here, Intel, Microsoft, Google. Google recently gave us $80,000 gift, but most of the others are really funding. So we're looking at, and this is what you do, you immerse. And the toy is extremely important. Our toy here is $400,000 PIV and that kind of stuff. Materials are important. 24 students graduated just in immersion cooling. Two-phase, that might be of interest to you guys here. There's something called PFAS in December 2022. Intel stopped making those fluids, so there's a great opportunity and a great challenge as well. This is a new lab we created, $2 million, just equipment alone. This is on cold plate technology. And importance of undergraduate research, I can't tell you how important it is. Really important. This is one of our undergraduates, Utah, giving a talk. Here's a veteran, you know, and doing some research, and actually wrote a very nice letter after he got a job, his dream job, and wrote to the president, wrote me a nice email as well. And this is, we recently got a funding for $2.83 million, ARPA-E funding. And creativity, very important. I don't want to dwell on it. And this is a very important slide here, right? And this is NJIT. I was right there. Actually, I took a picture with some of your team. NJIT won an award at the last NAI. I think, Jamie, you know that. And this was President Lim actually in a panel, in the president's panel, right? This is when, and it's all about students. And this is, I was going to show a video of Abel Mizrahi got his PhDs now at Tesla, just got promoted too. And, you know, we're, you know, we get together, we have a lot of fun. We go to Dallas Cowboys, so if you ever come, I have to convert you. If you're a Giants fan or something like that, no, you got to be converted to a Cowboy fan, right? So, and I think our students win awards, right? This is recent. But we were in Interpack, this is about 30 seconds. Interpack 2022, we had about 12 papers. I believe in sending an army of people. Out of 12 papers, we won the Best Paper Award, the Intel Best Paper, and also one of the 3 outstanding paper awards. Yes, former student, Dr. Virender Mule, he's at Facebook or Meta now, and got a major award at a conference recently, all right? And this is the panels we're involved in, was a bunch of folks. So you know, being from academia, I probably can talk about 6 more hours, but I loved being here. Thank you, and if you have any questions, fire me. By the way, if there's a U.S. citizen that is interested in graduate work in nuclear, I have funding right now. I have funding for some other things as well. Thank you. Thank you. Yeah.
Just stay here.
Okay.
Thank you so much. Working. Testing. Oh, all right. So thank you so much, Dr. Aganofer and Mr. Cohen, for very, very stimulating talk. Mr. Cohen, if you come forward over here. I wanted to give our students an opportunity to ask our 2 esteemed speakers, distinguished speakers today, any questions you have, you know, for Mr. Cohen or Dr. Aganofer.
Please
Come on,
remember
this-
he has
this
the
is-
money. I don't.
This is your opportunity to talk. We discussed yesterday that this is a very special event for the students because it gives them an opportunity to learn the power skills to communicate and make a pitch to the executives. And that's why the format over here is just 3 minutes. 3 minutes you have to say, what are you doing, why you are doing, and why do I bother? What does the society bother about it? What is the potential impact? So here are the executive and a very esteemed academic leader. You want to ask some questions, you know. Come on, yeah.
I'd like to ask more about this Cowboys comment you said. You can't say Cowboys in New Jersey, or what's up with that, huh? Now we got to take you to a Jets game.
Is this on? Okay, yes. Go Giants. But my question is, what motivates you for everyone up at the panel now?
Oh, what was the question?
The question is, what motivates you in academia?
Oh, I can tell you what motivates me is every morning I get up because I know I got to work with some brilliant students, and I also feel a responsibility. Their life, where it goes, I have some role to play. So absolutely, it's the students that motivate me, and I also have a responsibility not to be behind, to be at the cutting edge. So the stuff that I showed you is a moving target. Robert showed you his company. I mean, all the artificial intelligence, all of that AI stuff. It's a moving. Robert, for your information, my daughter's a radiologist, and so she works with all those scan machines and so on and so forth. So it's a moving target. So you get excited about how do I keep up, and I'll finish it. Keeping up is being uncomfortable. If you're too comfortable, you're useless. That's why I tell my students, it's okay to be comfortable by, learning, and you don't want to be too uncomfortable, but always be excited about learning something, and also be multidisciplinary, like he said, like Robert said earlier. Yeah.
I'll give you two perspectives. I'll give you one from the industrial side. I'll give you one from the academic, because I sort of play both parties. I'll tell you from the industry side, healthcare is not where it needs to be. There are still people that don't get the best healthcare. There's still people that healthcare is too expensive. There's still people who don't benefit from technology. There's still people who get procedures and they don't get 100% satisfaction. So I am on that quest for 100% satisfaction. And anytime I see a new technology, I tell you, I am still excited in my career. I've been doing this a long time. And every time there's a new technology, you try to ideate, how can that fit? How can that address clinical issues not resolved by conventional technologies? And I'm fortunate enough to work for a big company that's millions of impact. And then I think sometimes if we don't do it, if we all don't do it, who is? Who are we expecting to do it? It's actually creative people, and it's a creative use of these technologies. By themselves, they're nothing, right? It's our use of it. And I want to be that person. I'm not going to sit back and wait and wonder. I want to be able to affect change in a big kind of way. And then let me give you another reason. Why do I get motivated to spend a lot of days here, where they could double my salary, but it's still nothing? I believe you're the future. And I'm not saying that, I know it sounds corny, but I do believe you're the future. You have a mindset and a thought process that is very different than the people I have that are even in their 30s and 40s. You have more of an open mind. You accept digital. You accept technology. You accept computer science in ways, if you think about inventing, your creativity and your mind is opened up in ways that some of us may be a little bit more constrained. And I want to be part of helping that, and I want to be part of helping you all, and I want to be part of a university that's a great university that I think can make changes, and you're really talking about societal impact, and maybe that's a more important legacy than anything else.
So I wanted to add to these two wonderful comments is the first thing that excites me the most is the potential of a student's creativity and innovation as a freelancer. As Robert, and if I could add to your comment there, as we grow, our risk management strategy changes. We take lesser and lesser risk and try to be, and particularly in industry and all those things, there is an inertia associated with the disruptive innovation to a certain extent to adapt the change. Students are free of that. You are freelancers. If we give you the platform, your imagination and your creativity and your capacity to innovate has no boundaries. But we need to, interact with you. We need to give you the forum. We need to allow you to grow. And that's what excites me most about academia, because academia builds the foundation of the long-term innovation knowledge base. What excites me to work with the industry is because industry brings the solution in the near-term innovation, right? So if we get the industry and university partnership, that's how we move the economy, we move the world forward in order to meet the challenges of whether they are technical innovation impact, whether they are societal innovation and impact, or whether they are market needs.
I want to inject just one. The CEO of Kodak, George Fisher, many years ago, he was on 60 Minutes, he was being interviewed. He said, there's this thing called digital coming. Does it have a place? He said, maybe. Now you see what Robert is talking about, how he's integrating AI, machine learning, and so on and so forth. You have to embrace it. You can't just say, you know what, I'm keeping my fingers crossed. This is not going to happen, because it's going to happen sure as rain, right? So how do you adapt new technology? I mean, you can go on and on about places what is that? Iridium. $6 a minute. Robert, you were going to buy that phone, right? $6 a minute, and never launched. The reason is digital came, right? So you have to be able to anticipate, how do I keep up with technology? If you don't, you'll surely be left behind. And you just can't be scared. Maybe you can make a comment on that.
Well, not even scared. If you look at all the companies that were pretty good companies, I just read a case study on iHeartRadio. iHeartRadio, it's whatever. So they decided 10 years ago they were going to make a single portal, and they're really not anything, right? They're just a portal for a whole bunch of different radio stations. And they never anticipated radio stations might give it away for free on their own website and bring people to their website. Now they're tens of millions of dollars in debt. And there was a model that did not evolve. That was kind of digital oriented. You could say the same thing about Facebook. Facebook tried to just do enhancements and not make a remarkable change. And likewise, so I think that's where it becomes standard. I'll tell you though too, unless everybody welcomes digital in their lives, it's going to happen regardless, right? Do you know in medtech, who are, if I think 5 years from now, you know who our #1 competitor is to Stryker? So many people will say J&J, things like that, right? You know our #1 competitor? It's going to be Google and Amazon. Amazon's going to want to inventory all parts and provide it at an unbelievable low cost. That's not going to be about quality of care. It's going to be about the cost of care, and that's going to disrupt the technology industry, and it's also going to change what success is for, say, an implant anymore. It's not about how good you feel. It's just that you don't go back for reoperation even if you're miserable at home. Google is compiling all your data right now on your Gmail. Google actually knows everything you're buying, by the way. Do you know when you get a receipt sent to Gmail, Google is actually analyzing that receipt for what your tendencies are, and you actually authorize the use of that. And so now when you think about profiling you as an individual, it's the world of digital. But now there are things, though, that are not this generic. So no one's got data off my equipment in the operating room. And by the way, Amazon's asked me for it. And I tell them that you could go take a hike. We know more about procedures than it's what you do with it. But the other piece that's most important, doesn't matter that Stryker is a successful 80-year company. It's speed of innovation. If you don't go quick and iterate quickly, you will lose. It doesn't matter how great a company you are, which is why I'm fortunate to create this new division and try to move. So that sort of motivates me as well. Just think about this. How many people, by the way, how many people are computer science, data science, cybersecurity people?
Yeah, there you go.
A lot of people. How many people are robotics, material science, biology?
The most biology sessions were yesterday.
Yeah.
There were like 60 of them.
So if you think about it, computer science folks, if you're in my business, though, you got to partner with robotics, right? And being able to do it. But computer science people, you're quite fortunate. You can get 10 people together in a garage now off a laptop, and you know the amount of data you can get. You don't have to build a factory. You don't have to do a lot of investment. And if you think about VentureLink across the street, you could just get 3 people in a small office, and you could get access to different data right off the NJIT website, and you could innovate and you can invent in amazing different ways. What I want to do is actually partner with universities that do some of this practical research, as Tom said, but I want data science on a robot. So I want the two to work together. And I want the robot to understand about biomechanics and how a person walks. And I want to partner them with the person in material science. The whole world is now this combination of it. And I think that's the part too with digital by itself, right, is one thing, right? Is how do you make use of all that fantastic information? I'll tell you, it's exciting times ahead. I mean, the journey you're all on, this is like super exciting, and it opens up a whole new aspect that we never could have conceived of before. We will probably have a more remarkable difference in technology and the use of technology in the next 10 years than we've had in the last 30 years because of digital.
Yeah. So there you go. You have aspirational vision from the industry to find the near-term solutions and the innovation that can accelerate the technology development and technology impact in the society. You have the academic research aspirations for the system on the chip and going beyond Gordon Moore and other obstacles, whatever it is bringing the capabilities in the future of creating the system-level solutions to unmet needs. So my question to both of you is that what message you would like to give to our undergraduate students to be able to interact with interdisciplinary stakeholders, because no technology solution at the system level can be brought to market without having the team of the different stakeholders who have different cultural biases, who have different way, and they speak different languages, so to say. How do you interact with the different discipline leaders and stakeholders? What message you want to give to our students so that they can become leaders like you?
Well, how much time you got? Okay, so I'm going to do this in a minute because then you know I got this other thing I got to run to. Instead of just looking at the technology and how to use the technology and what good a technology is, don't think like that. Think unrestricted. Think unrestricted. Don't think like that. Even though you may say, hey, I'm technology, I got this great, don't think like that. You should be thinking about, first, what problem do you want to solve? And when you think about what problem you want to solve, then you stay open-minded. And then you look at all the disciplines that may contribute to solving that problem. But I think this generation specifically should be the problem solvers. I think there's enough technologies, not a creative use of technology, gee, I thought about that. It's like, what problem are you solving? And then combine everything that you have at your potential to work on solving that.
Yours.
Yeah, I think that multidisciplinary is the way to go. I was talking about system on a chip a little while ago. I'm not a computer science. I'm not into electrical engineering, but believe me, I have to understand something about architecture. I have to understand something about interconnects. You were talking about photonics yesterday. I have to understand that the future direction, interconnects is really the biggest delay when you talk about microprocessors, so on and so forth. So photonics is going to be the next thing that's going to take it orders of magnitude faster. What do? I can't, as a mechanical engineer, sit and just say, I'm just going to let the problem be set up and then try to solve it. It doesn't work like that. You have to be uncomfortable and go learn. And I also think that hopefully that the senior capstone project will certainly be multidisciplinary. It should have people from business. It should have people from electrical engineering and so on and so forth. I think there's great opportunity. And those of you that are on undergrad, go knock on the doors of people that have funding from NSF and say, I want to participate in REU. not necessarily, I'm a mechanical engineer, but other fields. Be uncomfortable. You can't make it by just being very narrow. So thank you.
All right. Thank you so much. And we are very, very grateful for your comments and aspirations and a marvelous keynote talk. Let's give both of them a big round of applause. All right.
Thank you.
Thank you so much. All right, so I think this brings the keynote session to a closer. Our president is here if he wants to say some words to close the keynote session. Oh, okay. All right, thank you so very much. And let's thank our keynote speakers again. So, we have scheduled a small break, but before we do that, like a bio break or so to start our the regular session, I would like to request our board members to introduce themselves because they are the one who have enabled this particular program to this success. Of course, we all get great ideas, great aspirations, but if there are no resources available and no people to guide and mentor us, our potential success would be compromised or may not be reaching to the level that we expect or we target. So I'm very, very deeply grateful to all the board members who are here and some of them who are not here for their tremendous support financially and time and what they call time, talent, and treasure to support our students. And today that we have grown this particular program from like $20,000 to over $750,000 per year, that is because of the great support and the guidance from the board members. So with that, I would request our co-chair, Brian Kiernan, to start the introductions.
Okay. My name is Brian Kiernan. I graduated from this school. I graduated from NCE probably before you were born. In fact, actually, possibly before some of your parents were born. And like Bob, I'm also a member of NAI. I have about 30 patents, and unlike Bob's patents, you can't see what I do, and it's impacted everybody in the world because what we did is the fundamental technology that let these things happen, okay? Digital phones, digital cell phones. We provided the fundamental technology that is in every cell phone in the world. Every manufacturer, every user, everything. And like I say, you can't see what we did. You've never heard of us, our company, but we make about $1 billion a year in licensing fees primarily. And the stock is doing very well. It's about $100 on the NASDAQ. And I come here because I enjoy doing this. Yes, what is motivation? To me, motivation for what I did in my career was fun. I made sure I had fun no matter where I was or what I was doing, okay? And you get that fun in a lot of different ways. Sometimes it's from a technical challenge. Sometimes it's just from the people you work with. Sometimes it's from where you were working. I've been all over the world, 222 different countries in my passports, every state in the union at least 2 or 3 times, and I have had a ball throughout the entire process. And I like working with you guys because it's a lot of fun. And I hope you enjoy what you're doing, and I hope you get a lot out of this, and I look forward to seeing a lot of you again. Take care.
Thank you.
Thank you, Brian. This is Shashi Patel. I'm working for PSCNG manager, managing some large projects and also keeping some standards group intact so we can upgrade the systems for state of New Jersey, and then we can provide the reliable power source. But I like to see all of you presenting very challenging and interesting projects here. Thank you.
Thanks, Shashi. Good morning. My name is Gobi Rao. CEO of Phase Change Solutions. Welcome. Thrilled to be here, and great keynote presentation this morning. If Stryker doesn't inspire you, I don't know what will. If Dheeraj doesn't inspire you, I don't know what will. So thank you so much. Looking forward, yesterday we saw the quality of presentations was spectacular. So for those of you who are presenting today, can we do better? Yeah? Well, the answer is yes, absolutely. Yes, we will. All right. I don't want to cut into the break time, so let's continue the introductions. Peggy?
Good morning. I'm very excited to be here today. I've been on the board for 10, 12 years. We keep deciding when it was. I'm really looking forward to seeing all the presentations today. I had a company. I sold it successfully in 2016. It was my partner and I were across the street in the VentureLink building. We did marketing and marketing analytics and data science. Our clients were in the Fortune 100. And we really tapped into the resources of this really great university. I look forward to seeing everything and excited to hear about what you're planning to do.
Thank you, Peggy. Good morning. Mark Long, Executive VP for MTF Biologics, R&D, Clinical Affairs. We are recovering, processing, innovating, and distributing human tissues and human organs. So thank you for all the work you do and all the presentations. I'm here to learn as much as helping. We do have many NJIT graduates in our organization, both in R&D, quality, processing, and manufacturing. We had president in our wards last week to visit and talk about research. We provided grants to some of you as a researcher, and we're also offering co-ops. So if you're interested in traveling or commuting to Edison, I don't know where it is, but somewhere south of here, we welcome you. So again, looking forward to some great presentations.
Thank you, Mark. My name is Al Matos, and I have been in the energy infrastructure technology domain for the past 40 years. I look pretty good, don't I? I started my career in nuclear power engineering, building nuclear power plants here in New Jersey. From there, moved on to electric distribution systems with PSEG, and then went into also an international, about 10 years or so, internationally going to South America mostly, working in different countries down there. Went into technology, retired from PSEG, went into technology, to a technology firm. And interestingly, I graduated as an electrical engineer in 1981 with my major electrical engineering degree in power engineering with a minor in bioengineering. I really liked the bioengineering aspect of it back in 1981. Unfortunately, back in 1981, there really wasn't too many jobs in bioengineering. But what we see today and what we saw today, really, I wish I was 18 years old again and start that over again, because it's very exciting, and you guys have an opportunity, a real opportunity to make a big difference.
Hi, I'm Harry Moore. Own a little tiny company called Graybeard Solutions. It has nothing to do with my gray beard. I worked for 42 years plus 11 days as a Fed. I am a product of this place, okay, many, many years ago. Not quite as long as Brian, but one of the things that you'll find, I too was an NCE, it says on my degree, my diploma, but I'm kind of confused, as the professor here said, about multidiscipline. I am both an ME and a double E. My specialty in ME was fluids, and my double E side is in RF and high power. So, and millions of volts, megawatts, gigawatts worth of power and radiation, specialty antennas, explosives. The beauty of working for the federal government was I got to be in command of my own future. I was a hard driving individual, still am today, and I only work about 100 hours a week. In a few more years when I get to be 100, not quite Brian's age, but when I get to be 100, I figure I'll cut back to something like 60 or 80 hours a week. The only thing that I can really convey to you is talk to your colleagues, not just within your discipline, but be cross-trained and talk to your colleagues in other disciplines. Feel uncomfortable, okay? The other thing that I learned in life is that remain curious, okay? There are two types of people in the world, fearful people and curious people. Be the curious one, okay? You're gonna have a lot more fun doing it. Drive yourself, talk to your colleagues. The friends that you build now in your college career, I have guys who I went to school with here, and I still talk to them on a routine basis. We've grown up together, we've got married together, they had kids, I don't, okay? They're grandparents, and it's a great thing, this camaraderie that you get from NJIT. It really is, it's a lifetime of experiences. So, best of luck to you guys. One last comment. It is really, really important, and I don't remember if it was the professor or Robert who said this. Yesterday, some of the students skipped over what the problem is. They were so engrossed in getting through the material. Spend a moment about what is the problem? What are you trying to solve? That sets the course for your journey, for your briefing. Okay, that is most important. Take care.
Thank you. All right. Thank you again, all board members, for your time today and again giving wisdom to our students. Let's take 5 minutes, stretch our legs, and in the meantime, our media colleagues are going to set it up for the next session. Thank you. students. And right after that, we are going to start the major event of today. It's National Academy of Inventors chapter keynote speech, and that will be followed by the new members induction ceremony. And this is very important for the students, and I will tell you at 11:30 why it is important for you. So this particular time, let's start the session. And Kim or Susan? So the way the format is that, I'm just trying to repeat if you were not here yesterday, that you have 3 minutes to finish your presentations. It's strictly enforced 3 minutes. You have the timer in front of you on the big monitor, and the moment you will start speaking, my friends at the media booth, they will start the timer. So please watch that particular timer. When the timer goes to 0 and red, your mic will be cut off. So the purpose over here is not to embarrass you. The purpose is over here to help you learn the skill set that you need to make a pitch in a very concise manner to the executives, which you will need tomorrow. It doesn't matter whether you go work in academia or government or in industry. You will need that little attention spent time from executive when they listen to you. And if you are not able to make a sense to them or convince them, then they will do something else, right? So there's a attention opportunity and about 2 to 3 minutes when you need to make a case. And that's what we are giving you the opportunity to learn that skill set. This is something beyond the curriculum, beyond the classroom, that you get to speak in front of the executives. So Sue is going to announce the presenter who will be presenting, and also the next presenter. And the next presenter should be sitting on those chairs so that we do not have a transition time. So after the 3 minutes, there is no Q&A period. The student moves out of the podium in this way. The next presenter enters the podium from the left of myself here. And we continue the next presentation. There are a couple of things. Your presentation would be uploaded by the time your name is called. And there are the arrows. The forward arrow is the one which is on the right side button over here that you need to press in order to move the slide. Your slides are also projected here on the monitor that is on the ground. So just to make sure that if you don't want to, look back over there, you can look straight down and you will see the slide. Huh? Yeah. Okay. So the clicker has to be pointed this. Why don't you put the first presentation over there and let me show them. Okay, so, all right. Okay, so what happened here? Okay, all right. So if you move the pointer towards your right and click it, it should work. All right, so good luck to all the presenters today, and Sue will start us.
Good morning. Our first speaker is Polami Basu. Following her is Rituja Bhattacharya.
Sorry. It's not working. Okay, one second. I used Google Maps to avoid the traffic this morning, and just when I thought I had succeeded, surprise, I ran into traffic. I almost couldn't make it here on time. In this world of honks and traffic jams, we are stuck in a never-ending maze of traffic congestion, turning simple trips into long, frustrating journeys and wasting our precious time. The environmental damage which is caused by the exhaust fumes of the vehicles and the increase in the fuel consumption only adds to our problems. So join me as I show you how I tackle traffic congestion using graphs. The earlier models like the ARIMA and the machine learning models could not account for time and space features simultaneously. However, in the recent years, graph neural networks using deep learning techniques have managed to find a way to do this. What I have achieved here is an advanced graph neural network architecture which will hopefully help us say bye to traffic jams. This is a real map of a small part of New Jersey, which I've converted to a graph using GeoJSON. The nodes are the road networks, the edges are the road connectivities, and the node features are the average speeds. For input, I provide the average speed of the first 10 minutes of all the vehicles present in these nodes to the graph neural network long short-term memory, the GNN-LSTM model, which then gives me the average speeds of the 11th minute as its output. This model showed a significant decrease in the mean absolute error values on analyzing 50 days of data. Next, I plotted a graph of the true speeds versus the predicted speeds, true in blue and predicted in red. In the x-axis, we have the 150 nodes of the graph, and in the y-axis, we have the speeds. I noticed that at multiple places in the graph, there's a huge difference between the real speeds and the predicted speeds. Next, I analyzed the heat maps of 6 days of data. The lighter color here represents lower accuracy. I noticed that most of these inaccuracies are at the junction or the intersection points, the parts in yellow. I proved this using histograms, and I found out the well-performing and the bad nodes, and I implemented the graph attention network model on them. You can think of this as a number of chefs working together in the kitchen. Each chef or the attention node has its own specialty, and together they make a beautiful dish, just like these together create a much better model than before. Thank you.
Speaking is Rituja Bhattacharya. Following is Sagnit Chaudhary.
Okay, I'll start. Okay. Imagine waking up one day and finding yourself without a hand. A devastating reality millions of people around the world face. Simple tasks we often take for granted, like tying your shoelace, holding a cup, grabbing a bottle, or even holding the arm of your loved one, suddenly become monumental challenges and sometimes even impossible. This is a world where limitations overshadow possibilities, and the dreams of regaining that once lost dexterity seem to be out of reach. But what if I told you that there is hope on the horizon? What if I told you that scientists are on a quest to bridge that very gap? So today, I'm here to share with you that groundbreaking field of research that offers that very day of hope. Now, how do you navigate through your daily life without the ability to use your hand? That's where the need for this project comes in. It aims to model and replicate human hand skills and make robot hands. Now, the motivation behind this research is not just to provide a solution for people with physical disabilities, but also to improve the lives of the aging population, people with temporary mobility impairments, and in general, industrial applications.
Now, despite the advancements in robotics so far, most current generation of robot hands lack the necessary finesse, precision, and most importantly, contextual understanding necessary to perform delicate tasks, as they are often bulky with limited range of motion. And this limitation often hampers their utility in various domains like prosthetics and in general industry. And this is the precise challenge we aim to tackle with our project. Now, how did I actually go about working towards this goal? First step, I collected data from human fingers while manipulating objects. I used the leap motion sensor for this purpose. Second step, I used a technique called trajectory clustering, which is a technique used a lot in machine learning to analyze the data I collected and then build human model of the human hand skills. And finally, I am transferring these very skills into the robot hands via models, and voila. Now, this is an actual picture of how the leap motion sensor senses and captures human hands, and in this case, my hands. Now, here's a quick video I took for your reference. It's supposed to play. This is the kind of data that I have gathered so far. This is a huge amount of data, and currently I am incorporating skills I have obtained from this data into the robot hands. Now, one of the major challenges that we have to tackle is overcoming the complexities of human hand movements, noisy data, and inter-subject variability. Future work includes expanding the repertoire of human hand skills that the robot has to master. Thank you for your time.
Speaking is Sagnik Chowdhury. Following is Yusuf Kanan.
Good morning, everyone. My name is Sagnik Chowdhury, and I'm presenting on the effect of deepfakes on college students' political opinions. So deepfakes are pictures, audios, and videos manipulated by machine learning programs to create realistic content. They represent a novel vector for the spread of misinformation, and the goal of this project is to investigate the way that this content affects the political opinions of young adults. So over the past few years, machine learning techniques have become much more effective, and in turn, this has led to the software for making these deepfake content more accessible than ever before. Misinformation spread through social media has played a major role in politics also over the past few years, as we've seen with 2020 election fraud claims, as well as COVID-19 and anti-vaccination conspiracy theories. Audio and video have long been considered to be the most trustworthy sources of evidence, but this is no longer necessarily the case. So in my research, I collected deepfake and unmanipulated videos and audios of President Biden and former President Trump from the internet, and I created a survey with 3 parts. The pretest collected demographic information as well as prior political attitudes, and I used explicit and implicit measures to collect this. So for explicit measures, I directly asked them about how they felt about the former president and President Biden, as well as their opinions on the Republican and Democratic parties, and if they would consider themselves liberal or conservative. For the implicit measure, I used the implicit association test, which works based on the principle that if you have a positive attitude towards something, you'll be able to more quickly associate it with a positive trigger physically by clicking a button. So then I exposed the participants to deepfakes as well as unmanipulated videos and asked them to distinguish which ones were deepfakes. So, and then I had the post-test where participants were once again asked about their political attitudes using both explicit and implicit measures. Some participants were also in a semi-structured interview. So this is an ongoing project and data collection will finish soon. However, preliminary results show that participants had about 65% accuracy in distinguishing between deepfakes and unmanipulated videos. However, there's not a significant change in political opinion. There's a slight downturn in attitudes towards the Democratic Party. This is most likely because this is not in the real life context where people would be exposed over a period of months or years. So it is important that we understand how this new vector of misinformation can affect people, as it is already being used and will only continue to become more realistic. Future work should focus on other age groups, such as older people, as well as methods to train people how to avoid being fooled. Social media platforms should also create policies to deal with deepfakes. And I'm thankful to Dr. Wolf, as well as the HSRI program, specifically the Moonshot Grant, as well as Dr. Gopalakrishnan and my participants for their time. Thank you.
Speaking is Yusuf Kanan. Following is Jeremy Kurian.
So I can guarantee that many of you guys have experienced traffic on your way here today. So I will be using a machine learning approach to predict traffic speeds and traffic congestion in our roadways. Did you know that in 2019, $340 billion were lost due to traffic accidents, and over 30,000 people lost their lives? And the typical US driver lost 51 additional hours over 2021. So predicting traffic speeds will not only save more time in your everyday life, but it will also ensure an efficient transportation system alongside improved road safety. This will allow first responders to get to a scene of an accident significantly quicker than in previous methods. So although rewarding, the current approach does not consider spatiotemporal information when predicting traffic speeds. Our data set both considers the space time of the graph and the time-based data included in our traffic model. So in the beginning, we have a map, and we convert that map into a graph and feed the graph into a graph neural network and a long short-term memory network. The graph neural network will allow us to exploit the spatial features of our data set, while the long short-term memory architecture allows us to exploit the time-based data. The GNN LSTM architecture will allow us to predict traffic speeds. It creates a graph that will allow us to have a prediction versus true graph, as you see in the figure over there, and also create a heat map of the accuracy of our predictions. So I enhanced the graph features, and that allowed us to have a more accurate model. In figure 1, the predictions includes the speed of the cars, the timestamps, and the standard deviation of the average speeds alongside the number of cars. And that produced a mean absolute error of about 13. In figure 2, we see the prediction data without standard deviation and without the number of cars. And that shows us a mean absolute error of about 30. So I utilized a new form of GNN LSTM models, and we expect to see a more accurate presentation of them. In the near future, we hope to enhance the feature space even more and predict new things, such as the number of cars and more traffic congestion and accident predictions. Thank you.
Speaking is Jeremy Kurian. Following is Vignesh Nethrapalli. Jeremy Kurian is partnered with Ari Kamet.
Hi, my name is Jeremy. This is Ari, and our project is simulating patient behavior with machine learning. So what if we can predict patient behavior just by knowing their symptoms? Our project is mainly focused on editing our current simulation in Unity to better reflect each patient's unique symptoms and behaviors just by using their medical conditions. And we mainly are using our project by understanding the impact of the environment on patient behavior through simulations and supervised learning to improve and better patient experiences and treatments. So the background of our project is that we're using the Toptasi Asylum in particular as a case study, which is a state mental health institution in Istanbul during the time of the Ottoman Empire. And our project is mainly focused on updating our current simulation in Unity, which uses agent-based modeling, which our lab has developed in the past, where each agent has a specific set schedule of movements. And we're using machine learning, specifically supervised learning for our project, where a diagram on the right-hand side illustrates a basic procedure of it. So we first started by creating training and testing data by using generative AI to create a large amount of hypothetical patients. And each of these patients has a symptom set. After this, we worked with a psychiatric professional or to label three indices for each patient, including sociability, mobility, and impulsivity. After that, we researched various machine learning models and finally chose random forest classifier to train our model with. After training our model, we integrate our model into Unity to actually have individualized behaviors for patients.
Specifically, random forest works by generating multiple decision trees. This splits data using smaller questions and groups, and finally predictions are made by taking the majority vote of all such trees. On the top right of our slide, you'll see the high accuracies we achieved with all three models scoring about 70%. This is one example of a decision tree. For example, a patient that has schizophrenia would receive its appropriate sociability index by asking questions such as, is the mood change greater than a 5? Based on the answer to that question and other questions seen as boxes on the screen here, it either goes left or right down the tree until it comes to prediction. Multiple predictions from multiple trees are then all used in a majority vote to come to a final conclusion. Our research all culminates together in a streamlined workflow. First, data is created in our simulation, then gets sent over to our machine learning model, from which our machine learning model can assign 3 appropriate behavioral indices, sends it back to our simulation, and our simulation can model the appropriate behavior for that patient. Our project not only has the potential to predict patient behavior based on illnesses or symptoms, but is novel in that it can model various other health institutions. And in order to do this in the future, we want to add more symptoms and more indices into our models. We also want to include anonymous data from health institutions to better increase the accuracy and validity of our models. And I'll leave off with this. What if we could model the floor of an ER room after an unfortunate incident? Imagine the lives that could be saved, and imagine a logistical nightmare. Thank you to Dr. Ozadil, our research lab, including Surya and Vidhi and Socket, and HSRI. Thank you.
Speaking is Vignesh Nethrapalli. Following is Sohom Sen.
Hello everyone, my name is Vignesh and I'll be presenting my research in caption data generation for automated audio captioning. So automated audio captioning uses machine learning to create natural language descriptions of audio, and it can increase the accessibility of audio to people with hearing disabilities and even AIs. Unlike technologies like speech to text, it's focused on describing sound scenes, which include sounds and the relationships between them. For example, describing thunder and related sounds like wind and rain. The sound scene qualities of interest in our research are going to be mood and emotion, as you'll see. The problem is that high-quality caption data is scarce, and as a result, researchers have turned to synthetic caption data, which often lacks sensory information related to mood and emotion. This information can be really important to millions of people with hearing disabilities, and you may have encountered the vague description, music, in movie captions. This caption does not convey mood or emotion well at all, and so more descriptive synthetic captions are going to be needed for more descriptive audio captioning models. Recent research has used large language models like ChatGPT to synthesize new caption data, and existing research has also explored ways to determine the mood of audio clips. We propose combining these two strategies as a means to enhance existing caption data. ML models can be trained to determine the mood of an audio clip. This would be our data extraction stage. And models like ChatGPT can construct the captions, augmenting them with this mood information. This would be our data augmentation stage. And one example is if we have a quiet mood, we may get a caption like thunder rumbles quietly in the distance, whereas something more loud or chaotic would be thunder loudly booms nearby. We plan to evaluate our results using standard audio captioning metrics, as well as human evaluators looking for qualities such as accuracy and naturalness of the captions. So far, we've been able to reproduce the models for determining the mood of an audio clip, and even achieved slightly better results than in the paper we're working off of, and we're currently fine-tuning our ChatGPT prompts to include the mood information into the captions. This work contributes to emerging research in creating synthetic caption data for audio language tasks, and future work can follow similar strategies to include other sound scene information into captions as well. By producing mood-enhanced captions, people with hearing disabilities will be able to better understand the mood created by sound in whatever they're watching, and maybe models like ChatGPT will be able to understand the story audio tells through its predicted captions and emotions. And I'd like to give a big thank you to Professor Cartwright and the HSRI for the opportunity to work on this research. Thank you.
Speaking is Sohom Sen, following Dylan Tontat.
Suppose you're walking down the streets of Times Square with thousands of unknown people. Do you have the slightest idea among all these people, the one who might pose a threat to you or to the common people around you? No, right? But what if I tell you I'm working on developing such a model that can detect any suspicious human movements with the help of cameras already installed in public places and inform the nearest security force? Interesting, right? My model not only focuses on proactive security alert, but also focuses on elevating virtual reality, gaming, animation, and biomechanics by creating lifelike human avatars and immersive user experience. My model is based upon these two basic ones. Simplex stands for Skinned Multi-Person Linear Model X. This is a model responsible for the 3D recreation of a human body using beta and expression parameters. The second, Frank mocap, is basically a neural network model responsible for the extraction of beta and expression parameters from a given image. This is a simple flowchart which will help you to understand the flow of my model. Using a motion capture device, which can be a normal CCTV camera, the human movements are captured at a rate of 10 FPS. Each frame is then processed by Frank mocap, which extracts the beta and expression parameters. The parameters are then sent over to the Unity engine using socket programming. At the Unity engine, I'm using Simplex for the simulation of the human movements in a virtual environment. All the movements are further stored in a database where a pre-trained deep learning model is classifying them under suspicious and non-suspicious categories. The red box indicates the human figure inside the frame. Using Simplex and Frank mocap, I'm able to recreate the human model in Unity and superimpose it into the original one to show you how accurate my model is. The first row focuses on recreating the entire human body, while the second row focuses on recreating the hand modules only. My model does not only seamlessly extract the beta and expression parameters for the simulation of human movements in a virtual environment, it also uses socket programming for the transmission of these parameters from a motion capture device to my Unity engine. And finally, I have added my own layer of coding, which mimics the actual texture of clothes worn by them. My model mainly answers questions of security, but it can also be used for answering other problem statements, such as its implementation in the metaverse or even in the biomedical field. Thank you.
Speaking are Dylan Tontat and his co-presenters Salma Ghazi and Haley Patel. Following, Roberto Torres.
Imagine forecasting the weather. You use the data from the first 10 days to predict the weather of the next 3 days. You look at how your model worked, and then you improve your model to, again, predict the weather, adding in those 3 days to the weather data set, and predicting again the next 3 days again. With each iteration, you improve your model, and it just gets better and better at predicting the weather. This is the idea behind using iterative machine learning to parse through large data sets and improve predictions.
For those of you who are not familiar with additive manufacturing it is a manufacturing process that allows us to create computationally designed objects by adding material iteratively, hence add and iterative, hence additive. It is common practice for engineers to simulate this process in order to ensure that they are printing objects correctly. However, running these simulations on a FEM model typically are computationally costly and time-consuming. Therefore, we propose using an iterative machine learning simulation model instead. Machine learning techniques are able to expedite the process of developing and testing new manufacturing technology. This can greatly improve our product quality. Because there's not a lot of research available on the benefits, this leaves a lot of room for growth and overall optimization.
Our algorithm uses extremely randomized trees to predict the temperatures of 30 data points we call voxels. So we use an iterative approach, which means we gradually increase the training set to increase our accuracy. So for example, we'll use the first 200 points to predict the next 20, then we'll use the first 220 points to predict the next 20 after that, and so on until we get to the end of our data set. So we hope that this will maximize accuracy while minimizing defects. To measure the accuracy of our model, we use two numbers, the correlation coefficient, which we want to be as close as possible to +1, and the mean absolute percentage error, which we want to be as close as possible to 0.
Our training and test data was implemented in a pandas data frame object, which we then organized into 53 feature columns. These are essentially parameters that our machine learning model takes into account and includes the voxel's distance from the laser's intensity, the creation time of the voxel and its coordinating time steps, and the speed of the laser. Because additive manufacturing is a spatial temporal process, we must take into account the speed of the laser across different time steps. And in terms of our results, our iterative precision accuracy was about 96.35%, which is greater than our non-iterative baseline models, which means our predictions are validated. Just for reference, we implemented training data and used the decision trees algorithm to predict future temperature profiles. Thank you to the Honors Research Summer Institute.
Speaking is Roberto Torres.
Good morning, and today I'll be presenting my focus over this. Today I'll be presenting my summer research, which focused on a wall clumping robotic system for light and shadow-based interaction. The problem that we were trying to address was a matter of the unexploited light sensing technology that exists in swarm robotics currently. The significance of dealing with that would be to reduce the cost with open source technology. Our goals were to develop an algorithm that would be able to mesh with this open source technology so to sort of provide a cheaper solution. The background in swarm robotics is involved in managing large groups of robots and providing decentralized control systems for these robots, and to achieve, let's say, simple interactions. The method that we decided to go with, we divvied the work into 3 components, whether it be data collection analysis to develop our algorithm, the circuitry design, and the manufacturing of the physical robot. The way you decide to collect the data would be to use this open source RGB sensor, project varying colors, see the variation in our data, and try to create an observed model to converge that observed data to that model, and transform our data to match that observed model. Our results were that we did develop an algorithm that would distinguish color. We did develop an algorithm to distinguish color. is still in the process. It can only develop, it can only distinguish between 1 or 2 colors at the moment. And yes. And the purpose or the innovation of this work would be to provide more interactivity within swarm robotics and robotics in general, and to provide further outreach within the swarm robotics field for educational purposes, and also for research purposes, to provide a more, to reduce the space taken by swarm robotic labs. A lot of space is necessary to dedicate to provide demonstrations and also for storage purposes. I would like to thank the URI Provost Summer Fellowship and Dr. Petros for giving me this opportunity. Thank you.
So that concludes session 5 of our presentations. Within the next few minutes, we will begin the chapter launch and induction ceremony for our NAI members.
Can you put me on? Okay, all right. Thank you so very much for all the presenters. Please give them a big round of applause. Aren't these presentations so inspiring and wonderful, right? So, board members, you got your challenge moved one level up, right? So, like no lunch is free, so you got to work today. This is my great pleasure to bring the next event to you. And this event that I'm very, very proud as the feature event of today. This is the event of the National Academy of Inventor chapter at NJIT. We have a distinguished keynote speech that I will introduce in a few minutes, followed by the new member ceremony. So let me first give you the status of the National Academy of Inventors chapter at NJIT. We established this particular chapter in the summer of 2021, and since then, we have created an ecosystem from undergraduate level to staff, researchers, and PhD students, and the faculty, but also with the external stakeholders in order to promote the innovation and inventorship, but also bring the stakeholders into the collaborative research synergy and innovation partnership, which is the most important thing, as you heard from today, keynote speakers from industry as well as the academic leadership, that the innovation is not to be put on the shelf. Innovation doesn't have to be only published into the papers and then forgotten about it. Innovation is not something that you develop a great idea into the classroom, talk about with your friends, and then move on to something else because you got a job to do. No. Innovation is about passion. Innovation is about commitment. Innovation is about dedication. And innovation is about meeting the challenges to make sure that if you got a great idea that has a potential of transforming the society, addressing the market or societal or technology need, you follow through, right? And you find your partners in order to make it happen. And that requires a certain kind of network and the skill set. And that's why this particular program is all about, in order to make sure that you are able to convey your innovative idea, not only just to create the innovative idea, but also to be able to communicate that idea, make other people convinced to partner with you so that you can make that particular difference. You can make that idea, that particular dream come true. Like Robert, talked about. Even when the people join the industry, they say, well, I'm just doing what I am told to do. No, there is always a room. If you can pitch an innovative idea to your employer, wherever you are, you become an asset in order to move that organization forward. And that's what they want you to do. You become an integral part of the ecosystem of research, innovation, and its translation to market for economic development, for job growth, for societal impact, in order for our society to evolve. And the needs are endless. Every time you solve one particular problem, it opens the door for another one. And you need to create that aspiration going, right? So I'm going to talk about, can we put that? Okay, all right. So this is what we put together as the mission of this particular chapter that is aligned with the mission of National Academy of Inventors in order to promote innovation and inventorship, but also to foster the opportunities for students, faculty, and staff at all levels. So as I mentioned in my earlier comment today, I'm so passionate and so excited and so motivated about students. After my graduation, I started my career with industry, and then I moved to academia. Why? I could have made a lot more money in industry, not to just, I'm just kidding. But the passion to work with the student was something that was so much exciting to me that I see the student, when they are given the opportunity, they can move to the frontier that all the grown-ups in the industry or so on will hesitate to go there, because disruptive innovation is disruptive. It's risky, right? And the question is, what is the value proposition? Sometime when PhD students, they present, something over there, they were told, no, this is not a good idea because its likelihood is not that good. But you, as the undergraduate student, don't have that biases, don't have that particular fear. So that's what makes the creativity to another level. As I mentioned, we started this particular chapter in summer 2021. I am very, very grateful for the support from the National Academy of Inventors that every year we get faculty inducted into the National Academy of Inventors as fellow or as senior members. But we also have the faculty join us at the NAI chapter if they have invented something and their patent has been filed by the university. We bring them as the chapter member and then create that particular pipeline. We also engage our undergraduate student to make sure that they are mentored, they are inspired, and they are given an opportunity to learn the pathways from research, innovation to entrepreneurship through the NAI chapter Student Inventor Club. And today and yesterday, if you presented, you're not only competing for Dr. James Stevenson Innovation Award, you're also competing to become a member of the NAI chapter Student Innovator Club, which is a great accomplishment on your resume. Tomorrow, if you go to any particular employer or you put your resume together, it says, I worked on this particular project. I participated into the symposium, presented to the board. I was part of this competition, but also I'm a member of the National Academy of Inventor chapter at NJIT, Innovator Club. That carries, some credibility. So we love to have you more engaged. We love to have you ask questions. And like it was said by our keynote speaker, knock on the door of the people whom you want to work with, whom you want to network with, and learn the skill set, power skill set, to be able to present yourself in a concise way, in a aspirational manner, so that the other person or the stakeholders, whether they are from industry, they are from government, or they are from academia, or they are from any particular stakeholder group, that can bring the resources to you in order to make your innovative idea happen. It takes the whole team from different stakeholders group in order to implement or convert your innovative idea into the market validation towards the potential commercialization, so that your ideas can make a difference in the society, as you saw in the keynote speech today. So we started bringing the people together towards making the pathways or network and create an ecosystem so that they can talk about the societal concerns or issues or the needs, and develop a forum in order to address that, how we can make our societies sustainable and continue to grow. So we looked into the 3 different areas, and these 3 areas are the grand challenges that are selected by NJIT through the NJIT Research Enterprise and the faculty and the student about a couple of years ago. And that is environmental sustainability, the healthcare innovation, and the data or the information technology, data revolution and evolution of the technology, dealing with cybersecurity, privacy, cloud computing, next generation computing, so many things that you saw in Mr. Robert Cohen's presentation today that made that particular simulation happen. You also saw from the student presentations this morning that they were using for very, very important societal problem that kind of computation, that kind of information technology, the use of the multi-sensors or cameras or talking about the mood simulation. It's all data-driven approaches. So we bring that and into looking into that, how we could create the ecosystem in order to make those innovative ideas happen in these 3 grand challenges area. And then we started the first one on the climate change. That was in 2021. And we brought the stakeholders and the researchers from Princeton University, University of Buffalo, Rutgers, the industry, the carbon and a phase change solution, and one of the CEOs is sitting over here, New Jersey Commission of Science and Innovation Technologies, and also various other speakers along with the student, in order to make sure that we bring different perspectives from different stakeholders group into the discussion forum. Because one of the things which is important in order to make that innovation translation in the society happen is that we communicate and we understand how we are going to create together that collaborative innovation partnership to make that happen. We continued that. We talked about in the climate change about that what we need to do in order to address the sustainability needs for environment, air, sea, and land. The next one was in global healthcare, and we brought a lot of stakeholders and the researchers and industry partners, not only throughout this nation, but also international, from speakers from South Africa. We brought from Dakar and World Health Organization, and so on. So those speakers joined us remotely and talked about the global healthcare needs, which is very important because the world is so connected today that the healthcare issues are not isolated, are not regional. It is only the question that how anytime COVID has told us and taught us that all of the issues with the healthcare are global, not local. So we brought that. We talked about in that the point of care technologies, monitoring, and infectious diseases, and all those things that affect the society, not only for the healthcare, but also its economic sustainability. And COVID showed us that how the supply chain management and other things, got impacted just because of the healthcare outbreak. So we see that the whole big picture from environment, from data, from healthcare, they are all connected to the global economy and our well-being. We then continued on the cyber infrastructure. We brought the stakeholders and experts in data revolution, cloud computing, cybersecurity together, and talked about, today it was talked about ChatGPT. The question is, how do you accept the outcome of your AI models or any particular AI search engine in the contextual information? So is it trustworthy or it is biased? So there are a lot of things are going on in that particular direction, which is going to impact the society and the future technologies development. So we focused ourselves on that. And then the earlier 2 months ago, we brought all the collaborators in the state of New Jersey with all the universities and the stakeholders together to talk about that how we can create these partnerships in order to address the societal, the technological, and the community needs in those 3 areas. So there were 7 universities who participated with their chief research officers over here, and Govi, sitting over here, was the moderator of the panel. And we are continuing our dialogues in order to share the resources from all the 3 sectors, academia, industry, and the government. So just wanted to give an inspiration to our students why the research is the biggest industry in terms of looking into what we need for the society to evolve. The total R&D expenditure, and why do we need the industry-university partnership? The total research expenditure globally continued to evolve from 1996 to 2022, but at this particular time, in expected 2022, global R&D expenditure is over $2.5 trillion. 2.5 trillion. Out of that, the United States is the biggest shareholder with $680 billion. This is a little underestimate because the final figures are not there. So just think about 700 or 750, that's where we are in terms of the $1 billion, along with the new congressional bills that are coming over there. So it's going to continue to grow. This is a very insightful thing. And it says that among the different sectors, from academia, from industry, from government, who spends what percentage or what fraction of that $680 billion. And you see the biggest one is industry. $447 billion is invested by the industry. And that was the key point that I would like to connect with Robert Cohen's keynote speech today, because the near-term product development and the technology innovation solution, they may be based on from the academic innovation and the knowledge base, but they are brought into the translational market validation and market product development by the industry. And that's why if we wanted to move and accelerate the innovation translation to the market, it is very evident that the academia has to create a partnership with the industry along with the government and the stakeholders, because the implementation in the society, this is what COVID showed us, that there are certain regulations and the infrastructure that is needed in order to reach that particular technology to the every part of the community and the global community. That cannot happen without having the partnership of industry, university, businesses, and the government. And that's what we are here for. That's what I wanted to give you the message, because you are the future leader of our society, and you will bring us to that particular level of the evolution. So at this particular time, I would like to introduce our next keynote speaker. And so today, you heard from industry leader, you heard from academic leader, and now it is my great pleasure to present to you another leader from the academy. And the National Academy of Inventors is the academy of academies, because it brings all the stakeholders who are there to facilitate and support the innovation and inventorship translation to the market in action. This is the societal representation. So it's my great pleasure and honor to introduce you Ms. Jamie Renee, who serves as the Executive Director for the National Academy of Inventors. As Executive Director, she is committed to growing the impact of NAI through strategic partnerships and intentional member engagement, and making strides in reaching and involving underrepresented populations in the innovation and the invention ecosystem. Jamie has a heart for humanity and a mind for business, a very, very critical combination for our society to make to grow, but also for you to be inspired so that we can make a difference. She has more than 25 years of corporate and nonprofit experience, having served in leadership roles within Home Depot, OAI, the Children's Home, United Way, and Habitat for Humanity. Please join me in welcoming Ms. Jamie Renee.
I think we're going to take a photo. I heard there's an interruption. We're going to take a photo before I speak. Okay. Yep, and I think you're coming up here too. Oh, yeah. Okay.
Go get you.
Okay. Thanks, guys. Well, good morning. I think it's the morning, and I believe that I'm standing between you and lunch, which is typically not a good place to be. So I apologize, but I have a few things I want to share with you, and I'm incredibly excited to be with all of you today. Tom, can you hear me okay? If I look down, you can't, huh? Tom, Kimberly, Siobhan, and certainly President Tech for inviting me here, not only with what you do on the campus, but what you're doing in the innovation ecosystem. You deserve applause, and so I'm not going to ask everyone to applaud for you, but know that I am, well, they are, yeah. I celebrate you for I'm also glad to be joining you on your Innovation Day and to witness the induction ceremony that'll take place a little bit later. And I'm also excited to hear about the students. I was sitting at the table and just your young minds focused on problem solving, and then also the challenge that you have to communicate the problem and the solution in 3 minutes and in language that resonates with diverse thinkers and interdisciplinary minds is something that will help refine you for years to come and also give you the strength to translate some of that invention into the private sector. I'm excited about the chapter here because we believe at NAI that the chapter really is the place where you can bring so many different minds together, not only to learn together, to share together, but to celebrate one another. And we need to pause for celebration. And the chapter is a place not only to challenge you, but to celebrate you. But I don't just want to talk to you about what the chapter does for your university or what it does for your local community, about what I believe the chapter can do for society as a whole and also America. I was supposed to be with you yesterday, but my flight was canceled. And while I sat at the airport for 5 hours waiting for them to decide that the flight was going to be canceled, I found that instead of being aggravated, I was going to look at the gift of time, the time that as we get older, the thing we love the most, could be used valuable. And so what I did is I caught up on some reading and I caught up on some news and then immediately became depressed because anyone that is watching the news, that's the first reaction that we get, depending on the channel, is depression. And then I started thinking about what you guys were doing and that I was missing you and the activities that were happening in that first day. And I started to think about what was possible with our chapters. You know, the chapters were together, bring to getting motions in the back of the room if I'm doing something different, be more direct. All right. The chapter is a place where, you know, that you can come together and you can think through problems with people who are not from the same field that you have. They maybe have a different lived experience or perspective. There can be shared learning and collaboration. And when I look at what the world is facing from a problem standpoint, I'm reminded that it's great minds like you. I mean, I now learned my technology from a company that I don't even know, and my phone was invented from a face that's right here in the room. It's these minds like you, that solve the problems. Every time our world has faced major challenges, it was the brightest minds that came together and saw those challenges as exciting, fun, and weren't intimidated by them. And instead of hiding or denying or being restricted by conventional wisdom, they unleashed what was possible, maybe in part because of their youth or their youthful spirit, and they attacked it. And the chapter is a place to continue to foster that energy and that excitement with you, and to do it in a way in which you're not limited to your own thinking and your own perspective, but that you combine with other perspectives and other lived experiences, because I don't really believe that there's one truth. There's your truth and my truth, your perspective and my perspective, and when we come together and we walk around an issue, we're able to see it more holistically, and the chapter is a place to do. You're coming up, I'm assuming there's some mic issue and that's what you're coming to do, all right? Is that good? All right. Well, I'm used to being interrupted because not only do I have a very strong opinionated team, and not only do I work with the brightest minds, but I'm the mother of 3 teenage daughters. And so getting interrupted and getting back on track is not going to be a problem for me. But at any rate, I'm really excited about the chapter and what you can do, and I want to challenge you. I want to challenge the young people that are sitting here. It is easy to get comfortable with being with people that are in your field, that think like you, that look like you, that have the same lived experiences as you. But if you are truly going to be the minds, and you are, truly going to be the minds that bring us together and create solutions, you need to get comfortable being uncomfortable. Being with people that challenge the way that you see things, see them differently, have different perspectives and lived experiences than you. You need to come together with those individuals and be willing to be wrong because they have a truth or they have a perspective that's going to make the research that you do, the invention that you do, that much better. We heard from a presentation earlier today about how technology is creating solutions for implants that are relevant to the particular body, and that we have different ways in which our body aligns depending on the region we're in, the gender, the race, the ethnicity, probably the food we ate, the environmental conditions all influence that. In order for you in your respective fields to truly make a difference in society, you have to create solutions for all of society. And the only way to do that is to include those individuals in the research and in the projects. So as you form teams, I want to ask you, challenge you to form teams that make you uncomfortable. Form teams with people that complement your areas of weakness, the blind spots that you have. And I hope that you do that also through the mentors that you seek out, not those that just pat you on the back, but those that see the greatness within you, the weakness you may have, and they will inspire you to find others to complement your areas of weakness and push beyond what you even think is possible. Get uncomfortable. I think I heard that from a lot of people here today, that being uncomfortable is the best. Do you remember when you were uncomfortable and you said, you know, my bones are aching, and your parents probably said, you're growing, it's growing pains. Well, that is something that is true throughout life. If you don't feel ache, you are not growing, and the opposite of growing is dying. So get comfortable being uncomfortable, and you will continue to grow. And I want to challenge you to find ways to do that within your chapter, with all of society, not just those that look like you or think like you, but those who challenge you and will help make the products and the research that you're doing that much more enriching. You know, NAI was founded to promote academic inventors, but we don't just promote academic inventors now. We work with industry, and we also are working with those that are the enablers. It takes a team to make things happen. Whether it's the marketing team or it's the sales team, and I'm sure those of you that have industry experience can attest to this, that the researchers and the team of researchers is one component, but getting something from research into market is going to take a team, and NAI is evolving to include those people in those industries that help make academic research translate into the benefit of society. I brought with me a short video that our president and founder, Dr. Paul Sandberg, outlines the history of NAI, and he does it much better than I could. And since he's my boss, and when I get to shout him out, it serves me well. I'm going to show you the video rather than give you the history verbally.
From its colonial beginnings, invention has always been part of the American experience. The country itself was an invention. Not only a new system of government was invented, but a provision to protect the rights of inventors and writers was included in the Constitution, providing the foundation for an intellectual property protection system that to this very day thrives and has made American research and technology the envy of the world. Whether these inventors worked alone, for corporations, or for research institutes, their accomplishments and contributions to American society have been justly recognized, their interests represented, and programs to foster their innovations long in place. But what about researchers and inventors associated with academic institutions? Since the establishment of Harvard in 1636, American colleges and universities have been the source of important medical and technological research. Not always patented, but transformative nonetheless. In the last 40 years, there has been a real explosion of patented technology from this segment of the American innovation community. Despite this fact, the important and unique role played by inventors associated with academic institutions was underappreciated and unrecognized until 2010, when Dr. Paul Sandberg, then Vice President of Research and Innovation at the University of South Florida, had a lunch and came away with an idea.
I remember having help from my staff, and I said, if you have a US patent, you're on the faculty, staff, or student, and I would love to talk to you. Come and have lunch. We had 100 people show up, either faculty, staff, or students, 100. And we had this lunch, and they all felt the same way. They felt that, this was a side of their life that wasn't supported by academics so much, but yet it needed to be. Because if universities are going to make this impact, they're going to make an impact in helping companies, they need to understand the tools of the trade. And so we decided we'd start the Academy of Inventors of USF.
Dr. Sandberg shared his idea with colleagues from some of America's leading research universities and with officials at the United States Patent and Trademark Office. They all agreed that a national organization patterned on the University of South Florida model would fill a void and make a vital contribution. The National Academy of Inventors was officially founded and held its first annual conference in Tampa, Florida in 2011. A decade later, the National Academy of Inventors has over 4,000 individual members and more than 250 member institutions worldwide. Since 2011, over 1,400 fellows have been inducted into the Academy. The Academy has grown and expanded its impact until today, it is recognized as one of the nation's 3 premier inventor recognition organizations.
So that's a little bit about our history. I will tell you that we've grown since that video, and so we're at about 1,700 fellows now. Of that, 48 are Nobel laureates, and the surprising thing there is the most of our Nobels, they were fellows before they became Nobel. So we say that we've kind of got a knack for finding emerging talent and pulling them in and recognizing them. But imagine a time, and it wasn't too long ago, where academic inventors were shunned in some way, that the challenge of their peers to see them as both academics and researchers, as teachers and entrepreneurs, was too much. And so the journey that you go on, depending on the field that you're in, you may know who you are, but others will stand on the sidelines and question your moves and shout out critiques and decide that you are one-dimensional when you know that you're much more than that. So if you're a researcher, you can also be an entrepreneur. If you're an academic, you can also be an inventor. And there are thousands of people that have come before you that said, I will not be defined by the limitations and what makes you comfortable. I am a disruptor. You heard that word earlier today. I am a disruptor, and I am comfortable being in the uncomfortable. I am here to sort of break through barriers, and the Academy recognizes those mavericks. Our members, and some are here today, they are the most eclectic and interesting and fun people that you will ever meet. And I hope that you strive to be recognized by the Academy, not just because we would recognize you, but because we are a team. The Academy is across 250 organizations. We come together on issues of policy and politics. We create papers together. We advise institutions together, and we make pathways together. We are a team of inventors that know that great ideas need to make it into the marketplace, And so I hope that not only would you like to strive to be recognized by the Academy for what you do, but you would also like to lend your talents to the Academy and be a part of that global inventor network that is out there of what I believe is America's think tank, the brightest minds of our entire nation. We've got a program that I'd like the students to pay attention to because you have access to it. NJIT is a member organization of the Academy, and we have a mentoring platform called GAIN. And through your email address, you're able to access that network. That network connects you with all of our fellows nationwide that are participating as mentors. You can get advice in your field of study, career advice, and I want to encourage you to come on there. If there are faculty in the room, even if you're not an inventor, if you're working in the space and you have advice to give, I encourage you to join as part of your NJIT chapter and become a mentor on that platform. It's obvious that you care about our future and our future generation of innovators and that you're here today. And so I want to invite you to join that program, our GAIN mentoring program, and part of educating children, not just in, I say children, young adults, not just on your campus, but nationwide. So I want to invite you to do that. We also have an IP curriculum that we created with the Michelson Institute. It's free, and it has a certification. I will tell you that only 40% of people pass the certification because it's an incredibly challenging test. However, you can take the curriculum and the certification for free. You can find it on our website, and it will educate you on the fundamentals of IP. If you plan on protecting your ideas and commercializing your ideas, I encourage you to take this curriculum. Many of our universities, and actually 323 institutes, have benefited from this curriculum just this past year, are using it as part of their instruction, not only for students, but for faculty. There are many faculty that have ideas that they are publishing in white papers that then cannot be protected, that could be inventions, that could go out into the marketplace and benefit society. So we ask administrators to also look at the IP curriculum, not just for educating their students, but for educating their faculty as well. So I'm going to invite you to take a look at that. Again, it's free. Only 40% of people pass the test. So if you're up for a challenge and you think you're part of that smaller population, I encourage you to do that and share it with your peers in your social network. You want to be a good friend, you want to talk about what is exciting. Everybody has ideas, and we are entitled to the idea of protecting our ideas so that they can be commercialized, not just for monetary reasons, but because that is the way they make it into the marketplace. And so I want you to, on your social media, if you're commenting about something that you've read or something that somebody else is doing, talk about what you're doing and share the IP curriculum, and let's get it out there and get everyone aware of how to protect their intellectual property and commercialize it for the benefit of society. You know, I made notes. I don't know why I keep looking down because I'm completely off my script, which is pretty common with me. I don't tend to do well with staying in the lines or following a script, even when I write it for myself. I don't tend to do well that way, which is why the Academy is a great place for me. The opportunity that I have leading the Academy, I'm a strategic thinker. I am someone that brings vision to life. Dr. Sandberg that was on there, he's got over 170 patents. He founded one of the first, or the first, publicly traded stem cell company, and that doesn't even begin to explain the man. He's a pilot, he's a musician, he's published songs, and he tells an okay joke, although he thinks he's better at it than he really is. He's got somewhat good dance moves, but he's just an incredible individual, and that's true of all of our fellows. They are talented, exciting people who have great vision, and the one thing that I get to bring is bringing that vision to life. So just 2 years ago, the USPTO has always been a part of the Academy, but we didn't have any intentional plans to work together. And so what I ended up doing with the help of our board members is we structured a 5-year partnership with the USPTO to grow the number of underrepresented folks filing for patents in the United States. The way that we're going about doing that is first identifying individuals from the underrepresented population and bringing them in to ask them, and get this, it's a marketing question, where are you getting your information, what language, what imagery resonates with you? Because we believe we've already got exciting programs and services out there. We just think that we're not getting through on the channels to that population to invite them in. So we did a language study, and the results of that study will be coming out this fall. After the results of that study come out, then we're going to invite those individuals that participated, and there's numerous universities that did, to, is this timer broke or am I over my time? Because it's been standing at 3 minutes for at least the last 5 minutes. Okay. They just, because I'll keep going until you boo me off. And again, as having teenage kids, it won't hurt my feelings. I'll just keep it moving. But at any rate, we're going to bring those underrepresented individuals into the fold and then have them help us identify programs and services that they lead the creation of, and we address barriers that's preventing them from being engaged in the invention process. Because it's incredibly important that all of us have a seat at the table. And not only that we have a seat at the table, but that we're not forced to assimilate. Because too often we look at diversity, equity, and inclusion and we see it like a checkbox. We say, I've got enough of this individual at the table, or I've got enough of these types of individuals on the team, so I'm good. I'm doing diversity good. I'm doing equity and inclusion good. And in actuality, it's a term that people throw around without really knowing how to live it. And if you require assimilation on the team, then you're not benefiting from the diversity at all. And so we are looking for ways in which we can create best practices and roll those out so that we truly can benefit what is the foundation of America to begin with. We are diverse individuals that came together, and that when we leveraged our diversity at the beginning, you saw thrust in innovation and advancements in the economy, and it's only because we assimilate and we blur out what makes us so unique for our own comfort that we're not seeing the level of advancement that we could. So we're hoping with this partnership with the USPTO, not only would we invite every American to see themselves as an inventor, but in a healthy way compete with the rest of the nation to let them know that America is the place of invention. And we will continue to grow our GDP and our place from an economic standpoint nationwide. So that's an exciting partnership that we have. That's the economic side of things, and the competitive side of things. If you're interested in that, I'd love to have conversation with you about that. But in this process of being an inventor, and then I'll wrap up because I really at this point with no indicators have no idea how much time I've used, or if I've got 5 minutes. I won't keep you for the additional 5 minutes because again, I know I'm standing here between you and lunch, but be uncomfortable. Be uncomfortable and embrace struggle as the opportunity for you to learn and strengthen yourself for what's to come. My future, my children's future, is in your hands. It's in your hands. You not only are the future, but you're shaping the future. And it's not enough to say that you're going to be in the place in the future, that if you don't have the right mindset, you're not comfortable with working with people that are different than you, you are going to create a future that looks much like the world that you're complaining about right now. So if you want something different, then make sure that you challenge yourself to do things different than has been done in the past. And don't be comfortable being with people that are like you. Be exhilarated by the idea of challenging yourself, and don't be afraid of failure. I believe that those that are afraid of failure like the comfort of what is possible, and they never push themselves to the extreme of what they're capable of. So embrace failure. It's a sign that you're unafraid. You're unafraid to reach for what other people believe is impossible. The Academy is here to support you. We are here to fight with you, and we are here to celebrate you and recognize you. I am excited to talk to you about the Academy, but I'm more excited to learn from you. The more that I learn about you and I learn from you, the more that I can do to serve you and ensure that the space that you're in now and the space you're going to create in the future is supported by the National Academy of Inventors, and we are a service member organization designed to do that. So I want to thank you for what you've done to be in the room today. I'm sure all of you deserve applause, but I'm really looking forward to thanking you for what you'll do in the future. And I'm excited about the world that you're creating, not only for yourself, but for my children. And I want to thank you for pressing the boundaries and being inventors. Thank you. Oh. Pass out the phone. Mm-hmm.
Thank you. Thank you so much for very inspiring, distinguished speech. There are any questions for Jamie?
I answered all your questions.
I did. All right. So now it becomes very exciting part of the event is the new member induction ceremony. So I'm going to call the name of the new members of the National Academy of Inventors as is sponsored by the NAI chapter at NJIT. So please join me at the podium to receive the certificate from Ms. Jamie Renee. The first one is Mr. Robert Cohen. And I would also like to request President Lim. Yeah, and then we will have a picture there. Thank you, sir. Next is Laurent Simon. Taha Marhaba, and for Taha, the certificate is receiving Dr. Wen Jiang. Yeah. We're gonna clone you as Dr. Taha Marhaba. Dr. Genoa Warner. I should get that. Yes. Thank you. Dr. Shaheen NJIT. And Miss Laura Osorno. Laura? Just to let you know that Laura is receiving honorary membership as she is the in charge and the manager of the IP processes at NJIT. So if you got any innovative idea and file innovation disclosure, she's the person to reach out to. Thank you so much, and please join me in congratulating our new members of the NAI chapter at NJIT. Yeah, could we have a combined picture as a request? So all of the recipients, new members should come on the stage, and President Lim. We're going to have a group photo.
Honor to take pictures with you guys. I wonder what they do. You got this. Huh? Take this off so when we're talking, they can hear.
Hello? Okay. So this brings this event to close, and we have lunch. So this is the lunch break. I would request you to please pick up some lunch. And we should be back over here sharply at 1 o'clock. Thank you so much. All right. You are so good. Thank you so much. You are here right on the dot, 1 o'clock. So I greatly appreciate it. So please be seated, and I'm waiting for my board members. Okay. So this afternoon sessions are in the area of environment sustainability. So this is a great emerging area, very critical importance to the society. And I'm very excited to see these many presentations in this particular thrust area. So I'm looking forward for your presentations. I'm still waiting for my board members. Oh, running to the restroom? Okay. Because I didn't want to be unfair to the first presenter because we are scoring. Yes, I know. Okay. I think that we are okay. Huh? Okay. All right, let's get it started. Now I'm looking my assistant, Susan. Okay, Brian is here. Okay, so let's get it started. Again, all right. I'm looking forward to all of your presentations, and good luck to all of you. And again, saying that this is environmental sustainability thrust area. Sue, you take it over.
All right, our first presentation this afternoon is Omar Al-Zaman, and following him is Colin Akara.
Okay, should I start? Or, all right. My name is Omar. My PI was Dr. Eberhardt in chemistry, and my project is called Synthesis and Characterization of Ruthenium-Based Photosensitizer Compounds. So there's room to make more efficient dye-sensitized photoelectrosynthesis cells using ruthenium-based compounds as the photosensitizer, which is the part that absorbs light. And this has applications in making clean energy sources. And we know that climate change is a big problem nowadays. So, and non-renewable energy is a key driver of our climate change issues. So from a chemistry perspective, making solar-powered energy or better like solar cells is it's a big deal. So we wanted to make a better component of solar cells, which are photosensitizers, using ruthenium. The specific cell we're working on is called dye-sensitized photoelectrosynthesis cells, and they can be used to split water and generate hydrogen fuel. So photosensitizers, as I said, are one component of these cells. They absorb light, and then they trigger electron transfer reactions. And ruthenium is commonly used as the photosensitizer here. So we made a literature compound using literature methods, and then we attached novel ligands to it. So we attached, well, I'll go into that later, but we also did NMR spectroscopy to confirm what we made. The first step was doing a palladium-catalyzed cross-coupling reaction to attach phosphonate esters to the dibromo-BIPI, and then we added rubidium trichloride as a second ligand to make a ruthenium trichloride to make a ruthenium complex, and then we added a third ligand, which was phenanthroline. And that was the part that was novel. The first two steps were using literature methods, and then we hydrolyzed the esters to make phosphonic acid so that it can be attached to a semiconductor, which is the last step. So we were able to make one compound with phenanthroline as a ligand, and we're getting more data on it. However, we need to do a lot more ligands. So we planned on doing more, but we ended up doing only one. So there's more ligands to test, there's more data to get, and hopefully we can publish it in the end. I want to acknowledge all the members of the Eberhardt Lab and Langen Engineering for funding the grant. All right, thank you.
Speaking is Colin Akaro. Following is Rafiatu Bikiinga.
Hi, I'm Colin Arcaro, and today I'm going to be presenting my project, which is understanding the impact of solar, magnetospheric, and terrestrial weather on the ionosphere. So the goal of our project, my project, is basically to understand and characterize the cause of ionospheric variations. The reason why we want to look at ionospheric variations is due to the ionosphere's importance with regards to radio communications, longevity of spacecraft, and the health of astronauts. The results of my work are basically to show these ionosphere dynamics over a specific part in Alaska. So, since we're trying to understand variations on the ionosphere, a good place to start would be like, what is the ionosphere? The ionosphere is a region of the upper atmosphere, approximately 60 kilometers to 1,000 kilometers in altitude, with a large density of plasma. Plasma is a collection of charged particles. Since these particles are charged, that means they respond to both electric and magnetic fields. I'm going to be looking at three forces: geomagnetic forcing, solar forcing, and atmospheric forcing, which can actually affect the fields that plasma typically responds to. When plasma does respond to one of these forces, due to the large abundance, it actually causes a change in the ionosphere as a whole. This is referred to as day-to-day variability, or DTDV. The way I'm going to find this DTDV is I'm going to be utilizing the data set of the Poker Flat Incoherent Scatter Radar, which is also referred to as PFISR. More specifically, I'm going to look at four parameters of the plasma. I'm going to be looking at plasma velocity, plasma density, the ion temperatures, and the electron temperatures. The way I'm going to be using these parameters is I'm going to find an average day for each season. I'm then going to be using standard deviation to find certain effects after one of these forces occurred. So an example, I'm going to be looking at Hurricane Irma, which happened in late summer. I'm going to be finding an average day of the ionosphere in the summer, then going to be comparing that average day to a day where Hurricane Irma happened or just recently happened. That standard deviation can then quantify the effect that, in this case, atmospheric forcing had on the ionosphere. So some of my preliminary results, the leftmost graph I have is actually showing the average day of a winter of the ionosphere. It shows two specific altitudes of 275 kilometers and 500 kilometers. Since this graph, I've actually found the average data of every altitude, and the two right graphs show the same thing but in different directions. This allows us to examine the flow of plasma and like the direction it's traveling. From these two graphs, we were able to determine that there's like an eastward flow of plasma for this time period. So right now, where I'm at is I've found the average day for winter. I'm going to continue by finding the average day for the other seasons. I'm then going to continue to analyze the data sets to actually compare how the three forcings I mentioned affected the ionosphere. The results of this study will eventually be published into a larger collaborative study with other researchers and institutions. Thank you.
Presenting is Rafiatu Bikienga. Following is Melissa Biligi.
Hi everyone, I'm Rafiatou Bikenga, and today I'm pleased to present my research on the role of granulosa cells in phthalate toxicity. This study investigated the effect of phthalate on critical genes involved in reproduction. First, phthalate are a group of chemicals used to give plastics their flexibility and durability. They are found in everyday products like cosmetic, food packaging, medical devices, and even in kids' toys. We are studying them because we all are constantly exposed to inhalation, ingestion, dermal absorption, also because they have been found in human urine, milk, and serum samples, and have been proven to interfere with the body's hormone production, thereby causing health issues like infertility in humans. This research was done on female reproduction, and we need to know that the ovary is the female reproductive organ that produces hormones, and the granulosa cells are specialized cells within the ovary that support hormone production. Because we do not have enough knowledge on how these chemicals disrupt fertility, we are trying to fill this gap, and it's very important because understanding the mechanism by which phthalate disrupt fertility will enable scientists to find potential solutions to this problem. The goal of this research is to find out how phthalate and their metabolites interact with the key genes involved in hormone production in the granulosa cells. For this research, some granulosa cells were harvested and cultured for 4 days in the presence of phthalate mixtures and their metabolite mixtures. We then extracted the RNA from these cells, synthesized the cDNA, and used the technique called qPCR to quantify the different genes. We finally found out that phthalate and their metabolite mixtures significantly altered the expression of the key genes involved in hormone production in the granulosa cells. These results are very important as it sheds light on how these chemicals disrupt fertility, and it also shows their potential implication in disrupting our overall well-being. The next step will be to publish these findings and also promote safer alternatives for consumer product and industrial practices. Overall, this study suggests that phthalate and their metabolite mixtures have the potential to alter the key genes involved in critical hormones production. With further research, we may identify safer alternatives for these ubiquitous chemicals and thus ensure a sustainable future for everyone. Thank you.
Speaking is Melissa Bilgiiti, and then following is Leah Marie Bouquet.
Hello everyone, my name is Melissa Bilgley, and my project was on the computational analysis of a nitrogen-8 stabilized single metal atom catalyst, referred as SMACS, for the electrochemical reduction of carbon dioxide. So as carbon dioxide levels in the atmosphere continue to increase, the detrimental effects it has on our planet are beginning to prevail. Therefore, there's an urgent and demanding need to develop and advance significant processes that can remove and convert carbon dioxide into other useful molecules. However, there are challenges because of the reaction's high overpotential and low selectivity and reactivity. So there's a demanding need to find low-cost catalysts that can overcome these challenges while driving the reduction forward. So the reduction reaction happens in an electrolytic cell utilizing proton-coupled electron transfer steps. And this process is efficient because it utilizes low-cost electrical energy. And the catalyst I focused on was this N8 support with a palladium SMAC attached to it. And these catalysts are newly emerging in the research field because of their high performance, low cost, and very unique properties and structure, but more research needs to be done on them. So over the summer, I analyzed the performance of this catalyst on the pathways to useful hydrocarbons and found the Gibbs free energy for the most stable intermediates by using density functional theory calculations. By analyzing the Gibbs free energy diagrams for the production of carbon monoxide and formic acid, they can be efficiently produced. However, it was unexpected that formic acid is easier to produce than CO. It was also concluded that this reaction is not spontaneous, as the first protonation does require an energy input. From CO, methanol can be efficiently produced where the most desired pathway is the blue one shown there. And methane can also be produced, however, we learned that it was highly unfavorable due to the very large energy barrier. But this is good because even though methane has its uses, it is still a greenhouse gas. By evaluating how pH could also affect the reaction conditions, it was analyzed that this reaction proceeds better under acidic than basic conditions. And overall, our reaction adding excess hydrogen to the system, we learned from all of our results that it does not improve reaction efficiency. So overall, from our results, we learned that the N8PD SMAC is efficient for the CO2 reduction and significantly lowers the cost when compared to metallic palladium. And this work can be used as reference for experimental design and synthesis for future successful catalysts to combat the challenges of climate change. For future work, I want to look at transition states, run solvation tests, applied voltage, and try out different SMACs. I want to thank the PSEG Fellowship for funding, my advisor, Professor Young, Professor Wang, and Mo Lee. Thank you for listening.
Presenting is Leah Marie Bouquet. Following would be Robert Bush.
Hello, my name is Leah Marie Boak, and my presentation is titled Space-Time Studio, Interdisciplinary Collaboration in Studio Between Industrial Designers and Engineers. Industrial design is an extremely interdisciplinary field with product designers working with mechanical engineers and manufacturers, among others, to develop products that will greatly benefit the user. I was setting out with my project to answer the questions, how interdisciplinary is the education to prepare students for the industrial design industry? How are colleges teaching industrial design relative to engineering and studio pedagogy? And how are they innovating their approach to design education? I did this with regard to studio because studio is the heart of design education, and it is the course where industrial designers really learn how to solve problems applicable to the real world. Industrial design is a relatively new field emerging after the Industrial Revolution and mass production. Today, there are around 75 institutes of higher education that offer industrial design as an undergraduate degree, and I'm researching 40 of them based on the cross-reference list of top universities from a couple different sources. I'm using a mixed qualitative research approach and using content analysis, using data coding on a spreadsheet, categorizing into 4 different areas: school information, general curriculum requirements, design studio information, and interdisciplinarity, and then creating charts and graphs based on that information to share my findings, and selecting schools with unique approaches to interdisciplinary to further research as part of an ongoing research project. I found many results. Some of them were interesting to me, were that several schools really emphasized interdisciplinary with education in their major descriptions, but only 2 offered an interdisciplinary studio with other majors outside design that allowed interdisciplinary in the actual projects. I found that MIT and Stanford house their industrial design departments under the engineering schools rather than the schools of art and design, showing that they are innovating design education, as they're the only 2 schools that I found that do that. This research is meant to be part of an ongoing research group that establishes a database of information on schools' design curriculums, provides alternative examples to traditional design pedagogy, and lays a foundation as a future growing body of work on how to maybe best innovate design education. And I would like to thank Gabrielle Esverdi, my advisor, and Kaveh Sami, a PhD student, for their help in my project. Thank you for your time.
Speaking is Robert Bush. Following is Gigi Chen.
A solar flare is an intense, bright eruption in the sun's atmosphere, like the muzzle flash of a cannon. They are a vital part of space weather and the coupled Sun-Earth system, especially in understanding properties of the plasma that allows for magnetic fields to reconnect and explode energy into flares. I'm Robert Bush, an Institute for Space Weather Sciences RAU student. I will be focusing on how energy is redistributed during solar flares in two significant ways. A sunquake, which is a helioseismic event on the solar surface triggered by particle beams from flares in the corona, the outermost part of the sun's atmosphere, that travel down to the solar surface, otherwise known as the photosphere, and transfer their energy into pressure waves. Then, extreme ultraviolet waves are large-scale disturbances in the corona that occur with either a solar flare or coronal mass ejection, which is the actual cannonball of ionized particles in the cannon analogy I mentioned earlier. Our main objective is to find relationships between sunquakes, EUV waves, and CME events and quantify these patterns into plots and histograms. Already having some of this data calculated, we use various catalogs of sunquakes, EUV waves, and CMEs and perform statistical analyses using Python to find trends between sunquakes and EUV waves, distinguishing them using their GOES flares class. More recently, we compared the times of each event in the EUV catalog and CME catalog, only considering an EUV wave to have a CME if the time difference was less than 90 minutes. Using the provided data, I plotted several histograms. Notably, figures 2 and 3 imply common events were associated with lower power sunquakes and had smaller impact areas. And figure 1 reveals that EUV waves excited without a CME, which is currently unexplained, had slower speeds and likely came from a different source, supporting an important prediction by my mentor, Dr. Stefan. This significance actually relates all three events, as the current theory is that the mechanism that excites sunquakes is the same one that excites EUV waves without a coronal mass ejection, except that the particle beams accelerated by a flare without a CME penetrate only the chromosphere, or the middle section of the sun's atmosphere, rather than the solar surface. And this absorbed energy in the chromosphere heats the plasma, which leads to greater pressure and thus an EUV wave shock. We also speculate that smaller sunquakes impact areas are linked to EUV waves by reducing the amount of energy that reaches the solar surface, meaning lower power sunquakes can be associated with EUV waves as some flare energy is concentrated in generating those waves. For future work, we will be using time-distance diagrams as shown here and finding their slopes to calculate EUV wave speeds and comparing these speeds with measured CME energy and masses by making scatter plots. Here's my acknowledgement.
Presenting is Gigi Chen, following Austin Dalton.
Sorry. Okay. Hi, my name is Gigi, and this summer I worked on the electrochemical degradation of PFOA using high surface area electrodes. So, what is PFOA? It is one of the many PFAS, or per- and polyfluoroalkyl substances, that are persistent and bioaccumulative in our environment due to their strong and stable CF bonds, making it hard to be degraded naturally. PFAS is also toxic to humans, causing liver and thyroid diseases as well as developmental disorders. And unfortunately, PFAS is commonly used in industry since polluting our soils, water, and food. Our lab has even detected PFAS in high intensities in food packaging, like in Burger King and microwave popcorn paper. So what is electrochemical degradation? It is when energy is applied to a system and it causes electron transfer, which directly oxidizes PFAS. Indirect oxidation via electrolytes that form reactive species have also been predicted to degrade PFAS. Additionally, degradation via electrodes is sustainable because it not only absorbs or filters PFAS, but actually breaks down these toxic chemicals. Scientists have been working to optimize working electrode by adding metal catalysts or increasing surface area. And on your right, you could see the predicted degradation mechanism using this method. I investigated high surface area electrodes because they're more affordable and accessible compared to some metal catalysts. And I first started by screening high surface area electrodes and then picking the one that yielded the highest degradation yield and then moving on to screening various electrolytes. Then I increased the electrolyte solution to optimize PFOA degradation. I used a 3-electrode setup submerged in PFOA solution, and then after degradation, I analyzed it using DPSMS, or desalting paper spray mass spectrometry, which is a sensitive and efficient method that allows for online ionization extraction and detection simultaneously. So my results show that RVC is the best electrode because it yields the highest degradation yields of above 80%. The best electrolytes is KCl and KNO3 because, as you could see from the table, it has the widest varieties of degraded intermediates, meaning that the initial PFOA concentration has likely decreased or been broken down. So based on these preliminary results, high surface area electrodes can become affordable, efficient tools for PFOA degradation, and the choice of electrolytes actually affects the mechanisms and degradation yields, and therefore should be studied in the future. Additionally, we have to test the reusability and scalability of RVC electrodes, and overall, PFAS pollution is a pressing problem because it involves human and environmental health risks, especially since companies are not removing them from their products. Thank you.
Presenting is Austin Dalton, following Annalise Dickinson.
Good afternoon. My name's Austin Dalton. Thanks to PSEG Fellowship, I was able to work underneath Matthew Cooper for the analysis of environmental dependence of HODI instrument calibrations. The significance of the problem that we decided to tackle is that the low Earth orbit satellite market is expected to see a huge increase in its value up until 2030. As a result, we should better understand the system in which these satellites are placed and how this system affects them through things like atmospheric drag. We do so by measuring the atmosphere with our instrument, HODI. HODI is a very sensitive instrument, and as a result, its calibrations can drift over time due to environmental changes. So normally, HODI would be controlled by an environmental control suite. We decided that since that's an expensive solution, we wanted to go a cheaper route in order to keep costs down. So we decided to use a Raspberry Pi as a central node to collect data from an Arduino sensor. This Arduino sensor picks up temperature, pressure, and humidity. We figured these would be the biggest factors that would affect our instrument and therefore affect the ability for us to ascertain what's going on in the atmosphere. Our preliminary results were to test that we can get measurements from this system in the time spans that we would be taking our calibrations at, and it is apparent that we're able to do that. As a result, our next steps will be to upgrade to 3 sensors or more, so this way we could account for directionality of the environment and how it would affect it through heater systems and cooling systems. And then we will be attaching it to HODI in order to be able to actually take laser calibrations and compare them to the environment so that we could see if there's any correlation between environmental changes and our ability to measure how the atmosphere is affecting or moving around. As a result, this will allow us to be able to better calculate satellite lifetimes and the cost of keeping satellites up in the atmosphere, and this will allow satellite companies to have an increased profit as well as a decreased cost. Thank you.
Presenting is Annalise Dickinson, following Nikita Dubinin.
Hello, everyone. My name is Annalise Dickinson. Large solar eruptive events have been extensively studied because their significant release of energy leads to easier detection. Coronal mass ejections and filament eruptions shoot high-energy plasma out of the atmosphere, evidenced by structures created in the sun's magnetic field called magnetic flux loops. It remains uncertain if and in what way the numerous and ubiquitous small-scale transient events, many filament eruptions, coronal ejections, and the possibly created small-scale magnetic flux loops correlate, and how they propel solar, wind, and solar surface processes, leading to the impact on Earth. Coronal holes are relevant to this study because they are areas in the sun whose magnetic field opens into space, streaming plasma out. The convergence of open and closed fields at boundaries create events that can escape more easily and reach Earth. Parker's solar probe detected many small-scale magnetic flux loops in the solar wind. So we wanted to figure out where they originated. We looked at coronal holes and found the coronal holes, which are the source of solar wind, and found coronal ejections with nearby mini-filament eruptions. To study these events, we looked at June 9th to 13th, 2020 during Parker Solar Probe's Encounter 5, and we looked at Encounter 5 because the Earth, the probe, and the sun were visually aligned in space. And so we looked at spatial and temporal correspondence between these events and identified conditional thresholds in which the events could be identified. These thresholds were subjective and depended on the visual identification of the explosive mass of the coronal ejections. Next, we analyzed the distribution in relation to coronal holes, and the boundaries were defined using the coronal hole identification via multi-thermal recognition algorithm, or chimera. Since the boundaries evolve over time, we merged multiple hours of data together to get one image per day. And in defining the width of the boundary, we offset on each side by the size of the coronal ejections range that was predominantly distributed within that size range. While we were not able to apply the numerical thresholds to all of the days of the encounter, we were able to refine the mini-filament eruption database from 33,000 events to 9,000 events. We merged repeated detections of singular events, and we also eliminated detections that were likely to be noise. So, for the event distribution in relation to coronal holes, we got the results that we expected. There were few events inside coronal holes, which means because they're less active regions, they're likely to reach Earth. And there were many events outside the coronal holes, but they were less likely to escape because of the closed field. There were numerous events around the boundaries, signaling that conditions caused events to occur and reach the atmosphere. Thank you.
Presenting is Nikita Dubinin, following Joel Duza.
Oh, sorry. All right. Greetings, my name is Nikita Dubinin, and I'm here to share my summer research project on blockchain technology and its use of plastic recycling supply chain. So the problem. Plastic recycling has been a significant problem to deal with, and yet plastic production isn't planning on slowing down. It is expected to triple by 2050, and as of 2021, only about 5%, or 51 million tons of US plastic waste was recycled. So the needs is since 2018, China has stopped taking any plastic waste exports, which means that majority of our plastic waste goes into landfills or burnt up for energy. There's only so much space designated for landfills, and pushing the boundaries with it might just harm the environment more. So my goals were to identify the potential opportunities and optimize plastic supply chain with blockchain technology, as well as understanding why it's important. So some background. Blockchain technology is an immutable digital ledger, which means that once a transaction is complete, it is recorded instantaneously and transparent, as well as can't be modified in any way. This technology is trusted for its traceability, encryption, and security. Now back to our problem. As you can see, in 2018, there is around 3 million US tons recycled, while about 5.6 million tons combusted, while the other 26.9 million landfilled. So my approach to this was I gathered information on this topic ranging from articles to research papers that disclosed the use of blockchain in plastic recycling industry. I needed to find current problems with with the recycling of plastics, and then any inefficiencies within the supply chain that can be tackled with the implementation of this technology in some way. So My methods consisted of research data analysis of plastic recycling data, including blockchain technology research reports. For my results, I found, here we go. For my results, I found that blockchain technology has the potential to fix problems alongside the supply chain with traceability of product, and as well as transparency across the whole chain. With its implementation, plastic problems such as greenwashing would be solved quicker than before. Some of the companies which have implemented blockchain technologies have seen decreases in production spending, as well as an increase in lifespan of plastics. Also, continuing, blockchain technology has the potential to solve certain problems in plastic recycling supply chain, allowing for a more profitable as well as environmentally sustainable product. The main focus is that the implementation of these technologies will require funding, but the profits will cover the initial cost of expenditure. A company called BASF has been applying a physical tracer for identification in plastic, while RecycleGo has been using a QR code-based system to keep track of the items. And I would like to thank NJIT URI Provost Summer Fellowship and my professor Junmin Jim Shi. Thank you.
Presenting is Joel Duza. Following is Sebastian Fernandez.
Hello, I spent my summer researching atmospheric mercury, specifically oxidized atmospheric mercury, which is a very potent neurotoxin. So a little background on oxidized atmospheric mercury. How is mercury first released? Well, it's first released as elemental mercury, and then it travels through the atmosphere, and it has a whole year time to go around and homogeneously mix throughout it. And in reactions that happen in the presence of sunlight, it is converted into oxidized atmospheric mercury. Now, this is important because once it's oxidized, it has a much easier time being deposited onto the land and oceans, where bacteria convert it into methyl mercury, which is its most toxic form for us humans, given that it's soluble in our fat tissue. So after it's converted into methyl mercury, it can go through a process called bioaccumulation, as well as biomagnification, where essentially it enters the food chain, and the further down it goes, the more concentrated it gets. And then it affects us humans when we consume food such as fish, for example. So the goal of my project was to investigate a couple of membranes that are used for oxidized atmospheric mercury adsorption. And what makes a membrane decent, membranes are first used for pre-concentration because its concentration in the atmosphere is so low that you physically cannot detect it in real time, so therefore it has to be pre-concentrated in one of the membranes. And that requires about like 2 weeks worth of time to do. So different membranes, they collect the mercury, and then what's important is that they are also able to release the mercury once they collect it, and they should be able to release it without changing its chemical identity, since that's what's important in the way that it travels through the ecosystems. So to do this, we used a ion drift chemical ionization mass spectrometer, that's what's unique about our group, because this allows us to distinguish between different species of oxidized mercury successfully. At the beginning, I spent my summer trying to rebuild parts of the mass spectrometer, as it had not been functioning for about a whole year. And after we achieved that, we then went into developing a oxidized mercury source by using mercury bromide as well as mercury chloride, which are similar to oxidized atmospheric mercury. And this is the design that we landed on, which consists of like a Boris plug and glass beads that are coated in the mercury salts. And the results of that were very promising because this shows that our source was very stable and that it gives a constant signal as we increase the helium flow that we use to carry it into our system. So this is an example of some results that we get from testing our membranes, and this shows the adsorption of mercury bromide onto a nylon membrane, and in respect to distance, that is exposed to the mercury. So these are a couple of the membranes that we plan on testing out. These ones are potential membranes, and these other ones are less absorbent surfaces, which are good to be used on experimental setups. Yep, I'd like to thank Dr. Kalazov and Laila Nashir, which is my lab partner. Thank you.
Presenting is Sebastian Fernandez. Following is Joel Florum.
Great.
Hello, everyone. My name is, welcome to my talk about Doppler residuals on a high-frequency radio link between Colorado and New Jersey. My name is Sebastian Fernandez, and this summer I worked with the ISWS REU program here at NJIT, and my professor was Dr. Gareth Perry, working with the Center for Solar and Terrestrial Research. A little bit of background on my project. HF signals, high-frequency signals, are used for long-range aviation, military, and government communications. The left figure illustrates how these high-frequency signals are transmitted by bouncing off of the Earth's upper atmosphere, also known as the ionosphere. This bounce causes these HF signals to be Doppler shifted, increased or decreased in frequency, by varying amounts throughout the day. As a problem statement, little is known about the mechanisms which actually govern this ionospheric variability, but studying yearly Doppler shift trends will make it possible to predict and even correct these modulations during daily communications. The goal of this study was to identify trends and a statistical model for the data to characterize it for future processing. My approach included an experimental setup of a radio link between a radio tower in Fort Collins, Colorado, named WWV, transmitting at 10 megahertz frequency. This signal is received by the antenna picture to the right, atop Faculty Memorial Hall at NJIT in Newark, New Jersey. Doppler shift in the 10 megahertz signal will be used for remote sensing of the ionosphere over daily cycles. This is an example of a day's worth of the data received by our antenna. Two regimes in the data are identified based on time of day. Early day observations are highly varied, while late day observations are more stable. This is related to whether or not there is sunlight above the ionosphere at the bounce location that I mentioned earlier. A histogram for a 5-minute section of the data shows that Doppler variations in the 10 megahertz signal are mainly characterized by a sharp peak at around positive 0.1 hertz. This positive peak indicates an effect of increased ionospheric density caused by solar irradiance. How can we further study these slices? These 5-minute histograms are fitted to a variety of statistical distributions. This slice recorded after sunrise was best fitted to a Cauchy distribution, which is different than the often assumed bell curve distribution for ionospheric observations. This fitting procedure was then repeated for all 5-minute slices throughout the day. This is a video that's supposed to play. This plot overlays the best fit statistical distributions for those slices over the Doppler shift readings from before. As you can see, a strong Cauchy correlation was discovered for data taken during sunlight hours. This trend of sunlight Cauchy distributions are consistent across all days of the year, and using this result, we can now better predict the ionosphere's modulation of high-frequency signals throughout the day. This will hopefully improve our ability to maintain steady, high-frequency radio communications into the future. Thank you all for listening, and thank you to the people who have made this program possible for me this summer.
Presenting is Joel Florum. Following is Olawanfumi Fuwa.
Hello, my name is Joel Florum, and I worked under Professor Pennock and Professor Djimijevic on a project called Monitoring Water Conductivity to Splash and Spray to Optimize Road Salt Use. So if you ever driven during the wintertime, you've probably seen one of these. They're called salt trucks. And as the name implies, they're trucks that carry salt and they spray onto the road. But have you ever wondered, where does that salt end up and why do they use so much of it? Well, salt is great for melting off the snow and ice to keep our roads safe. But if you use too much salt, there's negative impacts that comes along with it. It corrodes our roadway infrastructure, which causes billions of dollars in damage yearly. And also contaminates freshwater bodies and the soil, which contaminate our water. So we must know the optimal amount of salt we use so that we keep our roads safe, but also we minimize these negative impacts. And that's what our project aims to resolve. What we did was that we look at the residue of salt on the road and try to use that and find what's the right amount of salt we should add. So this is the breakdown. So as a truck is driving on the road, it picks up the water that comes off of its tire, and there's a collection box, and it sends that water to this conductivity sensor. This sensor reads the conductivity of that water, and the conductivity has a direct relationship between the salt concentration. The higher the conductivity, the higher the salt concentration the water has. So then we can use that data and inform the spreader so that only the right amount of salt is added onto the road. Now, this is not a novel idea. This is actually done before by a group named Nora Garrick. And he did his design with a metal box. And he was able to differentiate between a road with a high level of salt and a road with low amount of salt by looking at the conductivity of the water. But what he found is that there was a problem with clogging and there was maintenance issues. Therefore, I went on and made my own design using the mud flap of the truck. And this is a much smaller design, much more cheaper, and it's more easier to maintain. And so I used the NJIT Makerspace, and I was able to 3D print the design, and I was able to 3D print it and come up with this design. It doesn't have no pen, but don't get any ideas. But the good thing about this design is that it's like easy to maintain. There's like it's a small amount of parts, and so that and it avoids clogging. And what I want to do in the future is actually test this out on a truck or a maintenance vehicle, and then see whether it actually works in measuring the salt concentration and therefore keeping our roads safe, but also protecting our environment. I would like to thank the HSRI and the CE department. Thank you.
Presenting is Oluwani Femi Fuwa. Following is Saketh Gola.
Hello everyone, my name is Oluwani Fua, and I am from the Departments of Science and Liberal Arts. Over the summer, I've been able to work with my mentors, PhD student Lily Lee and Dr. Wen John on algae separation using recoverable magnetic particles under a tunable magnetic field. You might be thinking, what are harmful algae blooms? Harmful algae blooms are photosynthetic organisms and rapid growth of algae. There are simple plants that live in nutrient-enriched waters. They produce toxins, and its outbreak has led to the reduced quality of water. They also affect the ecological health of humans and aquatic animals. Although there have been different other methods which have been discovered over 40 years ago, these other methods are usually very costly and mostly time-consuming and energy-consuming. Our key hypothesis states that if we use a functional magnetic particle with high positive charge density, long polymer chain length, and optimal coating density, we will be able to improve the absorption of algae on magnetic particles. Our first procedure was to synthesize these magnetic particles by using ion chloride and adding it dropwise into sodium hydroxide and sodium chloride. After that, we coated these magnetic particles with cationic polymers to increase their interaction with algae in water. These cationic polymers are usually positively charged micromolecules, and they were labeled with different abbreviations such as PEI, CTS, and CTAB. We also measured the zeta potential of these magnetic particles in order to study their stability in water. Moreover, we cultivated microalgae in the lab in order to study their growth phase and also their optical density, and also to perform our algae suppression experiments. And to our greatest surprise, we discovered that these magnetic particles, which were coated with cationic polymers named PEI, were very effective on algae suppression. And you could see the table of like the algae growth phase which we conducted. Thank you. I would like to thank the HSRI for funding and the support, and also my mentors, PhD student Lily Lee and Dr. Wen John. Thank you.
Presenting is Saketh Gola. Following is Stephen Habeb.
Hello, everyone. My name is Saket, and today I'll be presenting on the impacts of cholera on the mental ill in the Ottoman Empire. So my project revolves around improving an agent-based model of an Ottoman institution called Toptazi Asylum in Istanbul. And a picture of one of its patient wards is shown on the right. And we want to basically model the impacts of cholera on the asylum through the outbreaks between 1894 and 1911. So studying the impacts of cholera on this project, studying the impacts of cholera on influencing the change of mental institution practices aren't well defined. So we can basically understand the role of contagious diseases in a historical setting. And the goals of this project are to model spatial additions to this asylum and accurately model an agent that's infected by cholera. And so agent-based modeling is often used to model the spread of diseases and other things listed over there. And it basically simulates the interaction between agents or individuals in a simulation and their interactions with the environment that they're in. And our project is novel because it uses historical data to model agents and in an environment that's not functioning anymore. And so our research approach was to model 3D models using Blender, a 3D modeling software, and also use data about the number of cases in the asylum, the number of deaths, and the number of recoveries from the disease. And we want to basically use C# scripting to modify information contained in JSON files modify information contained in JSON files to simulate an infected agent and to and then the results were to create a disinfection station, which you can see on the left. And on the right, you can see the model in Blender that will be added to the agent-based model. And just to go back to what I forgot, I just modeled agents in the simulation, and I colored them black and randomized which agents were infected. And then, sorry. And I'd like to acknowledge my advisor, Dr. Ozadil, for guiding me through this experience, and HSRI. Thank you.
Presenting is Stephen Habeb, following Michelle Joji.
Hello, everyone. My name is Stephen Habib, and I'm an undergraduate student in the Department of Biological Sciences. In this flash talk, I'm going to talk to you about the new project that I'm working on, which is perfluorooctane sulfonic acid, or PFOS for short, and its effects on the ovaries. So let's delve deeper in the captivating world of PFOS, a chemical residing within the bigger family of compounds known as polyfluoroalkyl substances. These human-made substances have infiltrated our lives, finding their ways in everyday products like non-stick cookware, personal care items, and water-resistant clothing. PFAS, including PFOS, are known as the forever chemicals due to the very strong carbon-fluorine bonds. These strong molecular bonds make it extremely hard to break down naturally in the environment, and thus it easily bioaccumulates in living organisms and water supplies. While PFOS is no longer manufactured in the United States, it's still persistent in the environment due to historical past use, causing health effects such as increased cholesterol, liver impacts, and immune suppression. My research focuses on the effects of PFOS on the ovaries because this is an area with limited scientific knowledge. Why is this important, you may ask? Well, let me tell you. The map on the left shows the levels of contaminations of PFAS in various parts of the United States. It can be seen that New Jersey is above the proposed limit set by the Environmental Working Group, which is signified by light blue in color. Additionally, you can see that Bergen County, New Jersey is ranked 4th in the most contaminated sites in the nation. Thus, this can be clearly noted this is a problem in our own backyard. Our hypothesis focuses on potential disruption of ovarian function due to exposure of environmentally irrelevant concentrations of PFAS. Ovaries, which are part of the endocrine and reproductive system, are crucial for women's reproductive health as they produce hormones, develop eggs, and aid fertility. PFAS accumulations in the ovaries can potentially distribute hormone communications and gene expression, potentially leading to infertility, which is huge. Our research is trying to understand how PFAS affects the ovaries and behaves as an endocrine disrupting chemical, so we can find ways to protect and keep the woman's reproductive health in good shape. During my summer research project, we investigated the effects of PFAS on ovaries. We used mice as model organisms and extracted their ovaries for the sake of the experiment. The ovarian tissue was then exposed in different concentrations of PFAS and a control for a duration of 96 hours. This was done for 7 cultures throughout the summer research program. For our future work, which will lead into the semester, we have planned to measure hormone levels and gene expression to determine if there are any abnormal changes. This is innovative because by studying the effects of hormone levels and gene expression, we can contribute to the knowledge about the impact of PFAS on ovarian function, reproductive health, and public health. I'd like to give a special thank you to Dr. Genoa Warner, Stephanie Martinez, the Honor Summer Research Institute, and all the members of EDC Lab. I'd like to thank you for listening.
Presenting is Michelle Joji, following Nathaniel Kaplu.
Hi, my name is Michelle Joji, and I will be presenting on the effects of nanoplastics on gene expression in the placenta. We produce over 400 million tons of plastic waste each year, and they end up everywhere, from landfills, virtually every ecosystem, and in our water, where they end up in our cells via inhalation, ingestion, and dermal contact. Understanding the effects of these particles on the human body will have implications in green chemistry, policymaking, and clinical medicine. The organ that I'm studying is the placenta. The placenta is a very understudied organ despite being critical during early development. For the growing child, it replaces almost every major organ and organ system. This means the heart, the lungs, the liver, the kidneys, and the immune and endocrine systems. Furthermore, it serves as an interface between the mother and the growing child. This research has only grown more relevant as recent research has discovered microplastics in our bloodstream and in every part of the placenta. This does not affect just public health right now, but our future generations. The purpose of my study was to identify the impacts of differently sized particles on the placenta. My hypothesis is that nanoplastic exposure will disrupt gene expression in the mouse placenta. In order to study this, we initially dosed pregnant CD1 mice with either a control 50 nanometer or 200 nanometer dose. These are reflective of environmentally relevant concentrations. After this, I extracted RNA from roughly 150 samples, and I'm currently creating the complementary DNA strand, which will be then used to conduct quantitative polymerase chain reaction, or qPCR, to analyze the changes in gene expression. This is expected to occur in fall 2023. As of right now, there isn't any concrete data. We expect the 50 nanometer dose to have a greater disruption to gene expression, however, due to easier entry into the cells. This fulfills a critical knowledge gap as little research has been conducted into this particular topic. Furthermore, we look to study other types of tissue, such as fetal tissue, in the future. Understanding the effects of nanoplastic exposure understanding the effects of nanoplastic exposure on placental growth and development, along with fetal and maternal health, will enable us to develop effective strategies to deal with the consequences associated with plastic pollution. I'd like to thank everyone that supported me, the HSRI, and all the members of my lab. Thank you.
Presenting is Nathaniel Kaplow, following Rahul Laha.
All right, well, hello everyone. My name is Nathaniel Kaplow, part of the ISWS REU research group, And with the aid of my mentor, Dr. Satoshi Inoue, and my co-mentor, Human Triton Nguyen, I'll present to you magneto-hydrodynamic simulation of coronal magnetic fields, evolution, and eruption. So a little area of my research. It has been widely believed that the coronal magnetic field primarily carries solar flares through a three-dimensional space. However, due to various observational issues, really not much is known about the 3D structures and dynamics of said coronal magnetic fields. Therefore, through magneto-hydrodynamic simulation, we're able to gap such knowledge. We're able to break through such not being able to know what. We're able to break through such gaps of knowledge and learn about all things solar flares. Again, let's talk about the goal and science questions. Again, our general goal is to understand the physics of solar eruptions from both simulation and observations. So how are solar eruptions driven? How does the magnetic flux grow during the eruptions, which again are the lines that form the solar simulation? And how are phenomena observed on the solar surface explained from simulation? Again, with the idea of 3D dynamics. Okay, so then we can talk about the approach that I took. So we first start off with a data file. This contains the initial condition and the boundary conditions. And we move to an MHD simulation code execution, which is parallelized for efficiency. But due to this, it's really not good to create visualizations at this point. It's really difficult. So again, we then move to what is known as an ANA, or merge code execution. And then we continue to visualization, and then success. We get some nice visualizations. Okay, so here's some preliminary results. As you can see, this simulation starts very close to the photosphere, the surface of the sun, and quickly propagates within a 3D dimensional environment. And then the next part would be to compare these results to observational data to learn more about solar flares. Now, you may be asking, why would I care about this research? Well, I like to ask everyone to take a look at the electronics they have around the room, phones, computers, the video camera recording me right now, as well as things such as low Earth orbit satellites, GPS, and even online banking transactions. All of these things, when given enough strength, enough power for solar flares, they can severely or even permanently damage these. So therefore, through my research, I gained to learn more about solar flares, how they propagate through, again, a three-dimensional space, and to be able to better predict and protect us from future solar flare events. Thank you.
Presenting next is Rahul Laha, and following is Adam Leszinski.
Picture this, a world where you can breathe in clean air. Look at blue skies, a world where your homes and industries can thrive without harming the environment. Seems like an utopian dream, doesn't it? But what if I told you that it's a tangible reality? We can harness renewable sources of energy, such as solar, wind, hydro, in an efficient manner, so as to meet our never-ending demand for energy, at the same time, saving the planet by reducing the carbon footprint. Taking into consideration offshore wind farms. Now, wind farms which are situated strategically in the middle of the seas, where the wind resources are strong as well as consistent. Now, these plants generate electricity at a significantly larger scale. However, there is a problem because there is no wireless communication medium between the offshore wind plants and the onshore headquarters. Now, if we establish a connection between these two, we can respond to system faults at a much quicker rate, at the same time, prevent damage to expensive machinery. The market demands a system of sensors that is attached to the real system, which would collect real-time data and upload them into a cloud server. Now, anyone can access this data from anywhere. Although, the SCADA model exists in the market, which also does the same thing for industrial processes. But the downside being that it collects data at larger intervals of time, and also it has no fault detection system. I have created an IoT sensing platform with optimal number of sensors along with microprocessor, which would collect real-time data and then upload them into ThinkSpeak platform, which is a cloud platform. At the same time, I have studied about Simulink and created a digital model, a digital simulation. The digital simulation is input the environmental factors such as temperature as well as irradiance, and now it can produce the output. This is known as the digital twin. The digital twin is basically a simulation model which could depict the performance of a real system in ideal cases. In my lab, I have conducted the experiment and created a circuit over a PV panel, although this model can be generated and made into a wind farm by changing a few parameters as well as the sensors. Now, from this system, the power is collected, and I have plotted the power of the real system in blue and the simulation system in orange. Now, I have generated my simulation model in such a way that the simulation output is equal to the real output, so that we understand that if there is a deviation between these two lines, we know for a fact that there is some fault in the real system, and we need to look at it. Also, this model can be implemented along with machine learning algorithms to create an automatic fault detection as well as a fault diagnostic system, further reducing the regular shutdown times for maintenance. Lastly, I would like to say, let us not merely imagine, but create a future where every gust of wind, every ray of sunshine has the potential to power our Earth sustainably so that we wake up tomorrow into a cleaner and greener world. Thank you.
Presenting is Adam Leszinski, following Emily Lau.
Good afternoon, everyone. My name is Adam Leszinski, and I am a chemical biology major from Stevens Institute of Technology. And over the summer at NJIT, my project focused on the absorption behavior of 6,2 of TCA to microplastics. So 6,2 of TCA belongs to the group of pollutants known as perfluoroalkyl acid substances, or PFAS for short. And similar to microplastics, PFAS are known to persist within the environment for a very long time and accumulate within living organisms. And so the significance of my research is in that PFAS is known to adsorb to many different materials, including microplastics. And so this creates a problem where living organisms that ingest microplastics also receive a more concentrated dose of PFAS along with it. And so my project hopes to observe the absorption behavior of specific PFASs to certain microplastics, in this case, 6,2 of TCA to polyethylene. So in order to prepare for my research, I looked into the literature to see how other types of PFAS had adsorbed to many different kinds of microplastics. And I also looked at literature that examined how PFAS can adsorb to laboratory materials that are made of plastic in order to keep my data as clean as possible. And so with my research, I hope to expand this body of knowledge. So for my approach, I made batches of PFAS and polyethylene in both glass and polypropylene containers. And I also created analytical controls with no polyethylene in them to monitor the background absorption of PFAS to the container which it is in. And these batches were, the concentration of PFAS within them was monitored using liquid chromatography tandem mass spectroscopy. So from my results, it is clear that 6,2 of TCA does not adsorb very well to polyethylene. This was what I predicted, in that 6,2 of TCA is somewhat anionic, which would mean that it would be repelled by the hydrophobic polyethylene. And so in the future, I hope this research helps to provide a point of reference for future research. And in the future, I also hope to examine the relationships of many other kinds of PFAS adsorbing to many other kinds of microplastics. So there are many different combinations of both PFAS and microplastic with many different kinds of properties that can create different results. And finally, I would just like to acknowledge my advisor, Sumbel Yaqub, and my advisor, or my PI, Dr. Mengyan Lee. Thank you very much.
Presenting is Emily Luo, And then following is Arman Manukian.
Hello everyone, my name is Emily. I worked with the NJIT ISWS REU program this summer, and I'll be presenting my research on forecasting solar flares using machine learning. So solar flares are eruptions of electromagnetic radiation and particles from the sun's surface. Lower class flares typically don't have much effect on us, but high class ones can have impact on radio communication, causing us to lose contact with satellites or power loss on Earth. Last year, actually, SpaceX lost over 40 satellites due to not considering space weather effects after launch, and this cost the company $20 million. There have been many machine learning models in the past for solar flare prediction, but a common occurrence across many of them is that they don't consider how the sun changes over time when making these solar flare predictions, which is an avenue that my group really wanted to explore and in order to improve these models. So many of these models will use sharp parameters as input. So what are sharp parameters? These are space weather properties believed to be correlated with solar activity. And so typically they're collected in like a 12-minute cadence, and many research groups will just use one singular timestamp to predict something 24 hours later. We wanted to see if we used more timestamps to see how are these properties changing within that frame of time to see if that can better help us predict solar flare index, an indicator of solar activity for a given day. Here's kind of a pipeline of how my tests ran. We ran 2 tests, one with a singular timestamp and the other with 4 timestamps, to see how the impact of the parameters would change the output. First, we had to balance the data set, so we used an algorithm to actually generate synthetic data points for the high-class flares, which are more rare. This is able to help the machine learn for these rare case models, which we care more about. And then we fed this data into a convolutional neural network, and then our output was the flare index. Here are some preliminary results, but my findings now show that there is a lower mean square error for when using 4 timestamps versus using 1, and that there is better performance predicting high-class flares when you consider the dynamics. And so overall, because we factor in dynamics into solar flare prediction, it can help us understand the underlying patterns that actually cause these flares to occur. We also work with data imbalancing problem, which is not only an issue in the solar region, but also in areas such as healthcare or natural disasters, because a lot of the time, the events that we care the most about are the most rare. And in the future, we actually want to include images in our prediction model, which would be a new approach into tackling this problem and can help us better understand and predict these large-scale events. And I'd like to thank my mentor and the NSF and the ISWS program for this opportunity. Thank you.
Presenting is Arman Manukian, following Layla Nashir.
Hello, this is Arman Manukian, and I'm a National Space Weather Science REU student, and I'm from Pepperdine University in Los Angeles, California, and my mentor is Vasil Yurchishin, who works at the Big Bear Solar Observatory with NJIT. So first off, what are solar prominences? So solar prominences are solar flares or bursts, if you will, that go outside the solar limb. And they can often turn into a phenomenon called coronal mass ejections, which means a lot of plasma from the prominence gets ejected out into the heliosphere, which surrounds the Earth and the entire solar system. And they're most visible in the hydrogen alpha, which is a deep red visible light, and other ultraviolet frequencies. So to get the data, I used a 4-inch full disk telescope, full disk meaning the entire sun, and then the data was processed with an IDL program that my mentor wrote a long time ago, and then I wrote a Python program in order to process the data into CSVs and to collect results. So the final product of the photo editing in the IDL program looks something like this. As you can see, the image has been colorized, and There's a clear solar limb that's drawn, which is the white line that you see around the sun, and there are also prominences which are clearly marked by the program. So what I hoped to do was to get the daily average number of prominences, and I was able to access CSV files to show this and write a program in Python. And I wanted to see how prominences correlate with solar activity, and I hypothesized that if the number of prominences on average go up, then the number of sunspots on average will go up. And the reason I chose sunspots specifically is more sunspots means increased solar magnetic activity. So it was the easiest way to measure if solar activity and prominences are correlated. And here are the final results. The dots are the monthly average amount of solar prominences. I originally wanted to do days, but I thought this graph looked cleaner and more clearly showed the data. The red line is a moving average with respect to the points, and the blue line is the same thing as the red line, but it's sunspots instead of prominences. And it seems that there is a clear correlation. And I couldn't have done this without my mentor, Vasil Yurchishin, as I mentioned before, and also my co-mentors who helped me throughout the way, Shu Yang and Taylor Baildon. They're also from BBSO. Thank you.
Presenting is Layla Nashir, following Human Triet Nugent.
So imagine you're at a restaurant and you want to try something fancy. Turns out, bluefin tuna. But guess what? That tuna might have high levels of mercury in it. How did it get there? Through coal combustion, elemental mercury is released into the atmosphere where it can stay there for up to a year. There, it can undergo photochemical oxidation to become gaseous oxidized mercury. Gaseous oxidized mercury has an easier time to go through deposition onto various environmental surfaces, one of them being surface water. And from there, mercury will go through the food chain and into your tuna. Preliminary data shows that around half of oxidized mercury will interact with aerosols in the atmosphere before going through deposition. I want to further the understanding of how the phase change of these aerosols will affect the reactivity with oxidized mercury. Additionally, I would like to understand the mechanisms and also measure the rate of oxidized mercury with solid and liquid surfaces. These aerosols are present in the solid and aqueous phase depending on relative humidity. In the solid phase, interactions are limited to the outer layer of this particle. However, in the aqueous phase, these interactions can occur throughout the whole thing. I expect that the reactivity of the aqueous aerosol will be much higher than that of the solid one, given that the whole particle will be involved in these interactions. In my experiment, I wanted to model the interactions of oxidized mercury on these aerosols. So to do that, I used a fast flow reactor coupled with a mass spectrometer to simultaneously monitor my reaction in real time and also identify multiple species. Additionally, to represent my surfaces of these aerosols, I'll be using ionic liquids, which are a special kind of salt that can undergo phase change in the absence of water, and also with small temperature changes. I'll be using mercuric bromide as my oxidized mercury surrogate. I ran solid phase trials on 2 different ionic liquids, as shown here. And I was expecting these solid surfaces to behave like one. However, due to the maintained reactivity, my results showed similarities with the aqueous surface. I hypothesized that this happened due to a thin monolayer of uncrystallized ionic liquid, which gave it its aqueous tendencies. In the future, I would like to modify my procedure to better eliminate this monolayer,
as in running my experiments under lower temperatures. Additionally, I would like to test the effects of salts found in marine and urban environments to better mimic atmospheric conditions. Lastly, I would like to thank Dr. Kalazov and Joel Duja and the McNair program for enabling my research this summer. Thank you.
Okay, correction. Hu Min Trit Nugent will not be presenting. We're going to move to Naya Pared. Can she make her way to the stage? Following Naya will be Jaiman Parekh. So the next presentation is for Naya Pared. The next one.
Hi, my name is Naya Pared.
Oh.
Yeah, that's the wrong one.
Okay.
Okay, there. Hi, my name is Naya Pared, and I was working with the ISWS REU program, and my presentation is on trigger mechanisms for solar flares. So for this project, we were attempting to determine triggers for solar flares, and we were doing that by first developing the procedure to measure reconnecting magnetic flux. Magnetic flux is just the amount of magnetic field moving through a particular area, and the converging motion of magnetic elements that move in opposite directions during the solar flares. This is important because solar flares have a big significance on power grids, communication, and technology, and it's important to understand what triggers them so that we can have a better understanding of their impacts on us. The goals of this project was to determine between magnetic flux and converging motion which one was the most important for triggering solar flares. So a little bit of background. Solar flares are huge explosions of radiation from the sun. They appear very suddenly and intense in a specific area, and they can last from minutes to hours. Solar flares produce radiation and charged particles, and the impacts can be auroras and geomagnetic storms, which can be beautiful to us on Earth, but if the solar flare is large enough, it can damage satellites and endanger the lives of astronauts in orbit. They can also produce coronal mass ejections, which can be very disruptive to our communications as well. Understanding these triggers is very important for space weather forecasting as well. So our methods were to first determine critical values for the solar flare intensities at a fixed wavelength. This would help us to define magnetic flux. Then we were determining converging motion for those elements going in opposite directions around an area during the solar flare with no magnetic field. After we determined these quantities, we would extend it to multiple hours for other solar flares. These are some of our results. Here we were experimenting with how the solar flare changes over time. This is for a 2015 solar flare. The first three panels show us the differences in time, and we can see the area changing. So the factors that we were looking for were magnetic flux and converging motion of the opposite polarity fields of the magnetic field. The quantities have been suggested as being very important in triggering solar flares. We want to determine which one is the most important, and we are currently extending this procedure that we've developed to 2 other solar flares to study and compare them. Yes, that's my presentation.
Presenting is Jaiman Parekh. Following is Varsha Rao Raisam.
This one's not mine. Yeah. Oh, for sure. Oh, okay. Hi, everyone. My name is Jamin Parikh, and the title of my research is Nonlinear Water Waves, Theory and Experiments. So a quick introduction to nonlinear dynamics. Nonlinear systems are a couple differential equations, and they're characterized by their seemingly unpredictable and chaotic behavior. They arise pretty much everywhere in math and physics, and there's no general way to solve a nonlinear system. On the right, you can see a double pendulum, which starts out pretty simple, but over time has very complex behaviors. In fluid mechanics, the subject of my research, nonlinearity arises due to surface tension and viscosity. Over time, these nonlinear effects become exponential, and they deviate a lot from an ideal model. So my research was focused on how vertically shaking a tank affects the waves generated. So we differ from past literature in that we include the nonlinear effects of surface tension and viscosity. So the way we conducted our research was by first inputting this system into MATLAB and running a simulation for certain frequencies, and then we would compare those frequencies into the tank that we created, and then we'd analyze the waves against the graphs that we have. So our results. What we found was that we have resonant interactions for waves of different frequencies. So a wave of 2 hertz, for example, can generate a 4, 8, 16 hertz waves. We also found the existence of periodic solutions, so simple sine and cosine waves, as we expected from periodic forcing. We're further investigating the effects of viscosity. So if we took something like honey, which you can see in this slide on the right-hand side, compare that to water, and we applied the periodic forcing to it, do we expect the same type of waves? And then we're also looking at incorporating higher order terms because nonlinearity is exponential in its error from an ideal system. So if we can include those, we can have a better approximation. And then finally, we also want to have higher resolution through an n-body simulation. So at the top on the current slide is our simulation, and the goal slide at the bottom is where we want to go. So some generalizations and applications of our work. Wind-generated ocean waves, especially those at high speeds, are very nonlinear. So by understanding how these propagate through the ocean and how they interact with each other allows us to create better naval architecture that's more stable and safe. We can also understand climate change better because energy transfer in oceans is driven by temperature differences, which mix viscosity, pressure, and density across different ocean layers. And finally, we can have a greater understanding of nonlinear systems as a whole, since some of the greatest open problems in math and physics are very nonlinear, such as that is turbulence. And then finally, I'd like to thank my professor, my lab partners, as well as the sponsors for the Provost and HSRI programs. Thank you.
Presenting is Varsha Ryo Ryasam. Following is Isaiah Rejoice.
Hi everyone, my name is Varsha Ryasam. I'm going to be presenting on nanobubbles-enabled foam fractionation for efficient algal removal. So coastal and estuarine hypoxia is a global environmental issue that causes harmful algal blooms, which negatively impact the environment, ecosystem, and human health. Our focus is on nanobubbles, which are bubbles that are less than 1 micrometer in diameter. So for a background, the current methods right now for water treatment include centrifugation, coagulation, membrane filtration, and air flotation. However, these current methods are energy intensive and have scalability and economic limitations. So we had 4 main tasks for the research. that I did, but I want to focus on the column setup. So if you refer to the diagram that I made, we first started with the column being filled with the solution spiked with the target pollutants, and then the ceramic membrane was placed at the base. And then the membrane was connected to the gas cylinder with an airtight PVC tube. And lastly, air nanobubbles were generated under pressure of 60 psi. So for some lab work that I did, I worked with the GC machine as well as DLS. So for results, we observed that there were two main types of foam. There was dry foam, which is polyhedral bubbles at the upper part of the column, and then wet foam at the base. The following graphs show a removal rate of two odor compounds. A is geosmin and B is 2-MIB. So the main results was that with increasing surfactant concentrations, removal rates increased significantly. At CTAB concentrations of 20 ppm, geosmin and 2-MIB removal rates reached 85% and 58%. Comparatively, SDS concentration at 20 ppm, removal rates reached 74% and 48%. Next, the results show that geosmin's removal rate did not significantly change as the pH rose or dropped, but the removal rate of 2-MIB did. The next graph shows that an increase in ionic strength caused a slight increase in flotation removal rate. So for future work, it includes using the optimal parameters from the lab on real lake water. And the anticipated impacts from lake water are that water salinity or hardness and natural organic matters may affect the behavior of odor compounds absorption onto the water-gas interface. And lastly, I'd like to thank my advisor, Dr. Wen Zhang, and my mentor, Yihan Zhang. Thank you.
Presenting is Isaiah Ray Joyce, following Hannah Shanahan.
The first half of July this year marked the hottest period in recorded human history. This level of anomalous heat endangers forest ecosystems by increasing the frequency of droughts and the damage they cause. Natural disasters like this turn otherwise healthy forests into dangerously struggling trees vulnerable to fire. And although scientists have expanded the complexity of modern land models for more accurate simulations, there still remains limited knowledge on how each specific factor impacts model accuracy. In this experiment, I tested the parameters typically linked with drought resistance, measured in evapotranspiration. The goal of this study is to isolate and identify the most sensitive parameters when simulating plant hydraulics and drought resistance. Every forest's ability to resist drought relies heavily on that site's dominant species, since their presence heavily impacts the ecosystem and health of the local habitat. As such, old-growth forests, like those found in the southwest of the United States, act as natural archives of successive changes in climate. However, collecting this data involves various financial and logistical costs, as trees and their mortality is still understudied. Furthermore, site-specific simulations require the extensive measurement and analyses of various characteristics, in addition to requiring a large array of laboratory resources. Rather than focusing on all of these traits at once, I will attempt to determine their individual importance in determining simulated drought resistance. I began by testing data in the Sierra Nevada forest in Southern California. The forest's dominant species, the ponderosa pine tree, is adapted for semi-arid environments, but is vulnerable to changing conditions in a settled area. Using data recorded from 2011 to 2018, I ran preliminary analyses of simulations to produce a baseline set of parameters to match the real-world site as accurately and consistently as possible. The model I used, Powerflow Trees, incorporates geological and plant hydraulics to simulate a forced release of water vapor known as evapotranspiration. I studied which parameters related to plant hydraulics and correlated to evapotranspiration. Running simulations for every incremental change, I compared the results to the observed data recorded at the site. As a final test of model accuracy, I ran simulations using different portions of the 8-year period of input data. My results found that the most sensitive parameters were the ratio of leaf to basal stem area to ground area, and the resistance to cavitation. Future research will focus on reviewing the significance of each trait individually and collectively in hopes of finding the most accurate and most optimal forest recovery plans. Finally, I would like to thank my professor, Dr. Shannon Tai. Thank you.
Presenting is Hannah Shanhinian. Following is Simona Sotiri.
Hello, my name is Hannah Shahinian, and my research project is on mercury sorption in propanotrophs. Now that's a lot of big words. Mercury is a pollutant that enters the environment through human activities like mining and burning coal. Methylmercury, the organic form of mercury, is a neurotoxin that can bioaccumulate through aquatic ecosystems. Humans are exposed to methylmercury when we consume seafood like tuna, which is why you're advised not to eat tuna every day. The transformation of mercury occurs mainly due to bacteria, which convert inorganic mercury into methylmercury and methylmercury back into inorganic mercury in a cycle. Bacteria are also known to absorb mercury, holding it in place and keeping it from bioaccumulating through the environment. Understanding this sorption can help us create new methods of bioremediation and help us understand the cycling of existing mercury in the environment. The goal of my project was to determine if propanotrophs, a type of bacteria already used in 1,4-dioxin bioremediation, could absorb mercury. If propanotrophs are found to absorb mercury, they could be used to treat sites co-contaminated with both mercury and 1,4-dioxin, which are two common pollutants. To test this, I chose two species of propanotroph, PHO6 and DD4. First, I mixed the bacteria with aqueous inorganic and organic mercury. Then I reacted the bacteria for various times. Next, I filtered out the bacteria. And finally, I measured the mercury left in the solution after filtering the bacteria. The less mercury that was left meant more absorption had occurred. For PHO6, the level of aqueous mercury decreased from around 1 ppb to less than 0.2 ppb in just 3 hours and remained relatively stable afterwards. Therefore, PHO6 exhibited fast and significant absorption of both types of mercury. Similarly, DD4 showed around an 80% removal of both types of mercury. Therefore, both species of propanotroph I tested exhibited fast and significant absorption of mercury. As a result, propanotrophs can potentially be used in mercury bioremediation, which is very useful for sites co-contaminated with 1,4-dioxin and mercury. Since most sites don't just have one pollutant but have multiple, having a bacteria that could knock out two at once is very useful in the field of bioremediation. Future research should focus on understanding the biochemical pathways of this sorption and testing this sorption in realistic settings, like those with co-contamination, with the hope of keeping our waterways clean and our fish safe to eat. I would like to thank Dr. Zhang and Dr. Lee's lab, along with the BioSmart RU, for this opportunity.
Presenting is Simona Sotiri. Is Luke Thomas here? Okay. So following Simona will be Carolyn Toledo.
Hello, my name is Simona, and in collaboration with my mentors, I worked on my project of exploring solar flares with the SolarDB cyber infrastructure. So our problem was that many solar flare movies in our flare database of NJIT's cyber infrastructure are either faulty or missing entirely. This would have detrimental effects on researchers in vast areas, and especially in NJIT's own Center for Solar Terrestrial Research. So my task for the summer was to work with this large data set and figure out the best way to add to the database. For some background, this database is part of a larger cyber infrastructure that contains other tools such as the FLAIR forecasting system that works based on the info in the FLAIR database. Based on the researcher's desired parameters, you can easily access any specific future movie. In the image on the right, you can see that the data in this database comes from observatories across the world, so it needs to be accessible as such. My approach to this research was to first organize the raw data using Python libraries based on its major features the database filtration system uses. Then, using code to decipher which files exactly were missing and comparing these results to the movies that didn't work in the database. Next, using IDL to download missing data from the JSOC data processing home and compile movies to upload. So the results that I ended up with were finding missing FITS files for 79 out of 189 active regions in the FLAIR database. The errors that I found with the movies varied greatly from being out of focus, having strobing effects, or even jumping forward a second, where their data wasn't there. Further, 52 out of the 75 regions had missing movies entirely, because the gap in the data was just too great. By using computer science models to give us statistical results, I was able to get a clear analysis of the problems with the database. Due to the various issues that each movie have had, we found little correlation between missing data and active regions. However, for the future, the step-by-step approach I created to add to and improve this specific database will continue to be in use to complete the FLAIR database, where I wasn't able to in my 10-week period. Also, deep learning tools will be developed for the early detection and forecasting of solar eruptions based on the information in this database. I'd like to give a special thank you to the Space Weather Sciences REU for this opportunity and everyone here who made this project possible. Thank you for listening.
Presenting is Carolyn Toledo, following Mallory Wickline.
Hello, my name is Carolyn Toledo, and with my advisor, Dr. Hannah Kumbioka, I worked on my project, an interactive VR AR museum experience to contextualize Van Gogh's artwork. So the main question that my project revolves around is how VR and AR technologies can be used to apply to art history and education in a new age of technology and culture. So my project uses state-of-the-art accessible VR technology to introduce a new standard for immersive learning. The main purpose of this is to use the VR platform to revolutionize methods of learning about arts and culture through visual means. As a visual learner myself, I know that a lot of people struggle to learn strictly through reading or other means. So my project utilizes visual information to help people learn more about museums. And the traditional museum experience is slowly dying out, as many people have noticed. There have been less and less attendees over the years, and it is usually seen as an outdated form of learning, especially as people lose their attention span in the digital age. So this project addresses that. So as mentioned, this project stems from the need for new ways of learning about works in museums. A lot of times museums attempt to offer context, such as wall text or plaques, but a lot of these are lackluster. And when museums do use modern technology, this often fails to create a fresh added experience. This image on the right here shows the Metropolitan Museum of Art's Chroma AR, which is an application of modern technology that does not successfully show a new way of learning. The process for my project was to create both a gallery that shows Van Gogh's work as one of the most artists of all time, as well as the asylum that he created most of this work in. So my process consisted of constructing each area and designing an ideal layout for navigation, prioritizing both visual accuracy and smoothness of an experience. So my result was a complete layout and a finished gallery ready for programming, paying attention to how the user is meant to navigate, focusing on spacing and overall design to prioritize user experience. So my project succeeds in doing what most similar projects in museums fail to, which is fully immersing an audience into a learning experience. And I gained a lot of personal benefits, such as proficiency in designing according to UX guidelines and other things for 3D design. Thank you.
Presenting is Mallory Wickline, following Catherine Wolf.
Hello, everyone. My name is Mallory Wickline, and I am a student at Penn State University here at NJIT on behalf of the RU hosted by the Institute for Space Weather Sciences. So my research this summer is concerned with jets on the sun, joint radio and extreme ultraviolet observations. This research is part of a joint integrated effort with researchers at NASA Goddard Space Flight Center to understand solar jet energetics. So what are solar jets? They are beam-like collimated plasma outflows that occur on the sun. They move mass and energy at these really high accelerated speeds and essentially contribute significantly to particle acceleration and transport. Through the magnetic reconnection process, jets lead to both high-speed particle acceleration and plasma heating, which we see as scientists through radio and EUV emission respectively. They outline these open magnetic field lines that go into the interplanetary space. So my project addresses how energetic particles are accelerated in solar jets, and then how energetic electrons are able to escape from the solar surface into the interplanetary space. To answer these questions, we had objectives of identifying and categorizing the source of energetic electrons during jets, as well as understanding their spatial distribution and energetics. This is important to study because the solar energetic particles associated with jets can have monumental impacts on space weather and satellite communications with Earth. There are also additional implications for jet-specific research in both astronomy and engineering as well. And there were essentially two main stages of my research this summer. First was creating a catalog of jet events over the last 2 years, and then selecting a few jets to perform a more detailed analysis on. The catalog itself yielded about 36 solid events with coverage from both remote sensing observations on Earth, as well as coverage from multiple spacecraft observing the sun. Instruments in total included instrumentation at NJIT's Extended Owens Valley Solar Array, the eCallisto Solar Spectrometer Network, NASA's Solar Dynamic Observatory, the Parker Solar Probe, the Solar Orbiter, and the Stereo spacecraft. We were primarily concerned with finding type 3 radio bursts and impulsive SEPs with these jets, both of which indicate the transport of energetic particles to the spacecraft and instruments that can measure them. And on this slide, you can actually see one of these jets. We have evidence of both remote-based and interplanetary type 3s with this event, in total covering radio, EUV, and microwave coverage. We need to understand electron emission from the jet site to piece together the greater picture of solar dynamics as a whole, which has value in understanding solar eruptions from different scales, from large-scale CMEs to transient spicules. Understanding the physical processes of solar eruptions for the sake of our time, health, and wealth is vital to humanity's prosperity on Earth, and we should put ourselves in a position of achieving a comprehensive understanding of our closest star and greatest source of interplanetary danger. I will be doing further work on just this. Thank you.
Presenting is Catherine Wolf, following Quentin Young.
Hello, everyone. This summer, I've been working in Dr. Mengyan's Lee lab with my mentor, Jose Antunes, and we have been uncovering the function of group 6 propane monooxygenases and Mycobacterium DT1, specifically on its ability to degrade 1,4-dioxane. So, 1,4-dioxane is a contaminant of emerging concern and is considered a probable human carcinogen by the Environmental Protection Agency. It has a 0.35 part per billion lifetime cancer risk. Despite no federal limits in drinking water, many states are setting stringent levels around this 0.35 part per billion limit. This means that there needs to be an effective and cost-efficient treatment method for drinking water. The goal of this project is to better understand how group 6 propane monooxygenases, particularly in DT1, deal with 1,4-dioxane and any co-occurring contaminants. Non-biological treatments are not suitable for this treatment. Granulated activated carbon and air stripping are ineffective, synthetic adsorbents are cost prohibitive, and advanced oxidation processes produce carcinogenic radicals. Biological treatments are effective, but so far unrefined. Monitored natural attenuation relies on native microorganisms, and these can be quite fickle. Bioaugmentation offers more control, but more information is needed on microbes, enzymes, and how they react in different environments to fully utilize this. Our overall approach is to use heterologous expression of group 6 propane monooxygenases and host Mycobacterium DT1 to confirm its function. We use techniques such as gas chromatography, flame ionization detection, PCR, gel electrophoresis, electroporation, enzyme restriction, and ligation to accomplish this. So far, we have successfully amplified the gene of interest, created a vector, and transformed the vector construct into MC²155. We have not yet confirmed its function of dioxane degradation. This graph illustrates our prediction of the rates of dioxane removal with the expectation that this is the sole gene utilized in its metabolism. By fully characterizing this gene, we'll be able to utilize it in contaminated areas to negate the cost and energy of ex situ remediation methods, have better control of bioremediation on sites, and allow for better outcomes. Understanding the initiation of dioxane metabolism is necessary for further research on the full degradation pathways to effectively remove 1,4-dioxane. I'd like to thank my advisor, Dr. Mengyan Lee, and my mentor, Jose Antunes, as well as BioSmart RU program for offering me this opportunity.
Presenting is Quentin Young.
Good afternoon, I'm Quentin Young, and before I begin, I would like to thank you all for listening until now, and I assure you all are at the tail end of URI presentations. Today, I present research conducted under Omoromi Sadik's BioSmart Research Group, electrochemical degradation of 1,4-dioxane by palladium ruthenium bimetallic nanoparticle material. 1,4-dioxane is a solvent used in chemical manufacturing of pharmaceuticals, detergents, and cosmetics, which ultimately ends up polluting wastewaters. Classified as a potential human carcinogen by the Environmental Protection Agency and a Group 2B carcinogen by the International Agency for Research on Cancer due to its tumor-promoting properties in animals, 1,4-dioxane poses a serious xenobiotic risk to environmental and human health. Due to the heterocyclic structure and its two ether bonds, 1,4-dioxane is resistant to biotic and biological treatment methods. Treatments such as activated sludge or microbial degradation are ineffective at quickly removing 1,4-dioxane from wastewater samples. Current electrochemical processes utilize advanced oxidative processes which have large energy and cost requirements and produce carcinogenic products are unable to be scaled industrially. Therefore, our research claims and aims to electrochemically degrade 1,4-dioxane by adopting cost-effective, greener techniques using ruthenium palladium bimetallic materials. Our research will utilize the techniques of chronoamperometry and cyclic voltammetry to understand 1,4-dioxane's electrochemical behaviors using a 3-electrode system consisting of a platinum counter electrode, a silver chloride reference electrode, and a palladium ruthenium drop-casted electrode. Analysis of the degradation progress will be used with gas chromatograph mass spectrometry, and chemical oxygen demand will be calculated and understood to help enforce the understanding of the pollutants' effects on the ecosystem and requirements for complete degradation. Further research on reaction conditions and the reaction mechanisms used in the catalyst and trials with real wastewater samples to view the effectiveness in an industrial facility setting will be conducted. I would like to thank Dr. Omi Sadek as my principal investigator, Dr. Francis Osonga, and PhD student Milad Tolapvan. Thank you.
Okay, so we are going to have the judges convene in ballroom B. Okay.
Okay, we have some additional presentations. Those are not to be scored. So I'm going to request you to stay in this room, right? And listen to the other additional presentations. I'm going to take the board members to the next room. We're going to talk about who are going to be the winners. So when we come back, we will announce the winner, right? Okay, thank you.
We're going to take a few minutes to give the judges an opportunity to transition. In the meantime, those who will be presenting at this point in this 3 o'clock hour, again, this list is identifying your order. Yes. Tendai Chimuka, you will be first. Justin Diaz is second. Jairo Leon is third. Samuel Levinston is next. Andressa Maragon, Isha Rai, Saad, and then Soham. That's the order. Okay? So whenever you guys are ready. Give us a couple of minutes, please. Oh, so you're number one. Okay, let me check and make sure. Can everyone hear me? We are going to begin the last portion of presentations. Presenting is Tendai Chimuka. Following is Justin Diaz.
All right, good afternoon, everybody. My name is Tendai Chimuka. I'm a computer engineering major, and today I will be presenting to you our scheme for 3D energy and collision-aware drone offline path planning. So as we know, UAVs and drones have been getting adopted into multiple industries, such as search and rescue and delivery. So imagine in a scenario where we have multiple drones operating in one airspace and following their own set of pre-planned flight paths. How do we prevent these drones from crashing into each other or colliding into one another? So as you can see from this image right here, it's a very simplified image. We have two drones that are operating in the same airspace at the same altitude, and they're following their own pre-planned flight paths. And as you can see, there are two collision points within the system. So what we did previously was our solution was to reroute each drone's flight path to completely avoid the two collision points, but that would also neglect one of the waypoints. So on a larger scale, this would leave a large amount of waypoints unvisited, which decreases the efficiency of the drones. So what we propose to do is to operate the drones on various different altitudes so that they're able to visit each and every waypoint, complete their objective while at least not crashing into each other. And this system is designed to be very to have like energy consumption and like in mind. So our progress right now, we're currently developing a model to test out the effectiveness of the proposed scheme, to test out the effectiveness of this scheme when we have a large amount of drones, then we'll analyze how many waypoints we were able to visit and how much energy we consume with this system. And I would like to acknowledge my professor, my PhD professor, Professor Rojas, and my advisor and the NJIT GS LSAMP Research Summer Program for funding me. Thank you.
Presenting is Justin Diaz, following Jairo Leon.
Good afternoon, my name is Justin Diaz, and this project is a preparation and characterization of composite hydrogel inks loaded with ceramics for bone tissue engineering. I worked on this project alongside my lab partner, Jang-Tae Kim. So bones have the intrinsic ability to self-regenerate and self-heal. However, there are situations in which bone substitution is required due to the severity and size of the bone fracture. Bone graft, donated human bone tissue, is limited in availability and can transmit disease. So, an alternative bone solution, which is synthetic bone substitution, comes in two types of ceramics for this project. The first type of ceramic is hydroxyapatite, and the second type of ceramic is tricalcium phosphate. So the goal of this project is to develop these two types of ceramics for 3D printing by using rheology to develop these two ceramics, by using rheology to characterize the flow properties, and using line tests to optimize printer pressure and speed. So these two ceramics are rich in calcium and phosphate, which makes them ideal for osteogenesis, the development and formation of bone cells, because they share many properties and the composition to bone material. However, they also need to synthesize itself with metacrylated alginate and phosphate buffer selene to develop itself into a novel composite hydrogel bioink for 3D printing. So for our research approach and methodology, we formulated three types of samples. The first sample consists of only metacrylated alginate. And the second sample is the synthesis of metacrylated alginate and hydroxyapatite, and the third sample is metacrylated alginate and tricalcium phosphate. So we used rheology to measure the viscosity, and we conducted line tests by using the 3D printer to print out all the samples in glass slides in S-shaped struts. So we use optical microscopy to capture the images of the strut, and then we use ImageA software to measure the strut width. We later calculated the average strut width and the standard deviation for graphing purposes, and this would later be used for further analysis. So if you take a look at the graph, tricalcium phosphate is more viscous than hydroxyapatite. It also requires higher pressure to print out the material. Now, the reason why viscosity matters is because we want to print out the material at a good flow rate, but make sure it keeps its shape retention after it is printed. So for future innovation, we'd also like to do further experimentation by testing the cell viability. And what cell viability is testing how many live, healthy bone cells are there after it is printed. For further work, we would also like to explore different concentrations, and all of this work would be done to verify which is a better bio-ink for 3D printing. So I would like to express my gratitude to Dr. Muir-Kirvandaran, the PhD students who I worked with, Nikki Rodriguez, Hadis Karache, and the contributions of my lab partner, Jung-Tae Kim. Thank you.
Presenting is Jaro Leon, following Samuel Lebeston.
Yep, good to go. Good afternoon, everyone. My name is Jairo Leong. My research team and I are focused on improving reactivity of ball milled aluminum powders using liquid metal embrittlement. Now, we are designing and manufacturing custom metal. There is custom metal powders. The reason is because metal fuels have higher energy density, but they burn relatively slowly. So our goal is to pretty much prepare aluminum powders with modified morphology. Now, we use aluminum because it's the most common fuel in solid propellants. Finer aluminum powders were developed to improve burn rate, but they have a reduced energy density and are hard to handle. So in that in mind, we pretty much, according to recent studies, use gallium to pretty much penetrate the grain boundaries of aluminum to help improve the reactivity of aluminum. So we prepare composite spherical powders through emulsion-assisted ball milling. We develop different milling protocols and to prepare these different powders, and then we characterize these different powders by using the scanning electron microscope and using particle size distribution. Now, we prepare these samples in a planetary mill using agate vials and balls, and we either mill aluminum by itself, or we do a 95% weight aluminum with 5% weight gallium. These are microscope images. The one on the left is aluminum as received. The one on the right is the milled aluminum. The one on the right pretty much is a lot more flaky than the one on the left, but these flakes do show a change in morphology in comparison to the one on the left. With this one, when we add the gallium, you can see that you see spears on the right, and the shape is more uniform and finer than the one on the left. So to further analyze this, we look at the particle size distribution. This graph pretty much showcases the samples from before. Aluminum as received is the gray curve, the flakes are the red curve, and the black curve is the spheres. So we pretty much prepared spherically shaped composites using emulsion-assisted ball milling, using liquid metal embrittlement. For the future, we aim to pretty much test the reactivity using thermal analysis tests, X-ray diffraction, and heated filament ignition tests. Thank you all. Thank you all for attending. Have a nice day.
Presenting is Samuel Leveshton, following Andressa Maragon.
Hi, my name is Samuel Levstein, and I'm working under Dr. Yoda Samizer to learn about the effect of background complexity on ensemble perception in video conferencing. Looking around the room today, I see a lot of faces that are neither sad nor happy, so I can say that the overall mood is relatively neutral. That's what ensemble perception is. Ensemble perception is a person's ability to judge summary statistics from a group of items. However, many studies that have been done on ensemble perception before have only been using very simple displays. I want to introduce background complexity to see how that affects ensemble perception. Understanding how this works will improve video conferencing technologies, which can then improve communication in telemedicine, online education, and remote work. In the past, it has been found that humans can very well understand the average emotion of a group of faces. They can also understand the mean size and speed of a certain group of items. However, many studies in the past have only been using face cutouts or very plain backgrounds, as you can see in Figure 1. They've only been using face cutouts to show to the participants. However, I want to introduce backgrounds, as you're always going to see something behind the person that you're looking at. In my experiments, we'll be using an eye tracker to limit participant field of vision, so that the participant will only see what you show them. We're going to be putting the more faces on various background conditions and see how that affects the participant's judgment. We're currently focusing on the morphing process, which takes a fairly long time due to needing a bunch of faces from the Chicago Face Database, taking their neutral and happy faces, morphing them, and then getting in between facial expressions. After this, we're going to get a lot of complex backgrounds, which we're going to be putting in the background of the person. We're going to be showing them 16 different faces, give it to the participant, and then run the experiment to see what they think the overall emotion of the entire group is. Understanding the need to know what background complexity does for ensemble perception is very important, as it relates really closely to real life. In a video call, you're always going to have some sort of background behind the person, so it's very important to know what the background does compared to rather just the face. Understanding ensemble perception and how it is affected by background complexity is important, as it could lower the need for travel due to more in-person meetings taking place due to this better technology. In the future, we want to include a lot of audio cues into our work, in addition to background complexity, to see how that affects ensemble perception, as you're always going to have audio and background in your video calls. I would like to thank Dr. Yoda Samizer and HSRI for all the support. Thank you.
Presenting is Andressa Marangan, following Isha Rai.
What is the scarcest resource we all have? Time. Time is limited. Time to spend with your family, to establish your career. Time. Time is the only true unit of measure. According to AI impacts, the world will reach its maximum computing power in 10 to 20 years, which means we need to reduce our carbon footprint. Hence, I introduced our nanostructured low-power memory chips, RAM, or resistive random access memory, which is a non-volatile memory that works by changing the resistance across a dielectric, which means that data will be saved even when the power is off. The video shows our fabrication process, which starts by having the substrate, which is the initial layer. Additionally, Each of the individual materials will be added upon by a deposition process. The last two layers, which is PT and TI, which stands for platinum and titanium, will be using a quantum dot deposition, which means that it will reduce the power, enhance the performance, and minimize heat. After fabrication comes characterization, which means we need to analyze the data. On the left and the right, there's two different pictures, which shows our results for the set and the reset for the nanostructured devices. Our results show a reduction in power consumption by 1,000 times. It's not an additional zero. This is huge. Our company, Quantum Nanotech, is in the process of moving this from the lab to the market. We have a provisional patent, and we're in the process of filing for the utility patent. This memory chip can be used not only in the semiconductors, but also in AI to increase its processing speed, in drones to maximize the flight time, and in aerospace for NASA to maximize the astronauts' resources. I would like to acknowledge NJIT, the NSF Regional and National Program, the McNair Program, the LSAMP, and URI. My name is Andressa Marangon, and thank you all for your undivided attention.
Presenting is Isha Rai. Okay, moving on. Saad Retmatullah. Going once. Okay, there you are.
Hi, my name is Saad Rahmatullah, and I'm a student in the Civil and Environmental Engineering Department at NJIT. I'm going to be presenting my research investigating the influence of water salinity concentration on thermal conductivity of soil. The problem I discovered quickly was that soil thermal conductivity data interpretation could oftentimes be overly conservative in engineering application. Thermal conductivity is critical in geoengineering, such as the design of cabling for a renewable energy project, which is what my research pertains to. There are also applications in piping, how you get your hot water, as well as oil and gas. I hypothesize that an increase in understanding the factors that affect thermal conductivity of soils will lead to more informed engineering design decisions and save costs in $1 trillion renewable energy market. This summer, I set out to measure the thermal conductivity property of various soil compositions at altered salinity concentrations. So why is this important? Currently, large-scale renewable energy project sites are being leased and developed at a rapid rate, especially in the Midwest. Transporting the generated power through cabling from these solar arrays and wind farms to develop cities requires geotechnical expertise, and a geotechnical engineer will measure the thermal conductivity of the soil on site in its investigation, which is how well the soil conducts heat. When these solar arrays collect heat from the sun, they generate electricity, and it's transported through these buried cables to a substation. You can see an example of trenches on the picture to the right, and these are the buried cables. Ideally, there's conductive soil on site that will be able to dissipate the heat generated through these cables that transport the electricity. Otherwise, the cables overheat and can cause brownout, setting these cables on fire. There's a case history about this that occurred in Auckland, New Zealand. An engineer will design thicker cabling through cable insulation to prevent this from happening, but it's an expensive engineering decision that can cost tens of millions of dollars across miles of cables. I used two soils for my testing. Sample A was really sandy from Putnam County, Florida, and sample B was a fat clay collected from Troy, Texas. First, I ran a sieve analysis on both samples and a hydrometer on sample B to determine the particle size distribution to classify these soils as sample A as sand and sample B as silty clay. My work treatment plan consisted of testing these soils under three main conditions, which were under deionized water, 15 grams per liter concentration of sodium chloride, and 30 grams per liter sodium chloride, which I did for both soils. I selected these values to model rain and post-hurricane salinity concentrations based on my literature review. I injected a compounded amount of the specific optimum moisture content, increasing in quarterly intervals, as well as the in situ moisture content. Next is me oven drying the samples for 24 hours at 110 degrees Celsius as per ASTM standard. Here's a table of each condition which I measured thermal conductivity at, totaling to 18 data points, each for sample A and sample B. Here's an image of my laboratory setup at an off-campus lab in New Jersey. And so my results found that water salinity for sand can increase optimum at 15 grams per liter of sodium chloride. And there was a drop down after using increasing the salinity to 30 grams per liter. For a fat clay, it was the opposite. It was increasing linearly, increasing the conductivity when I increased the salinity of the soil. This summer, I can move forward by testing more variety of soils, such as gravel or glacial till. I could also bring on an electrical engineer to help me interpret the data that I have. Thank you to the PSC&G Fellowship, the NSF I-Corps grant, and ANSGO and ANS Consultants accredited soil and material testing laboratory, where I conducted these tests. Thank you.
Last presenter, Soham Shashikumar. Is he here?
Good afternoon, everyone. My name is Soham Shashikumar, and today I'm going to be presenting my project on understanding the pathophysiology of persistent post-concussion symptoms with convergence insufficiency. So whenever you try to hold an object close to your face, your eyes have to converge or turn inwards to be able to see the object as one. An inability to do this is defined as convergence insufficiency. It can develop without any sort of prior cause or as a result of concussion. And in particular, in people who have concussion symptoms that persist for more than 30 days, they can develop what's known as persistent post-concussion symptoms with convergence insufficiency, or PPCSCI. We don't know much about the physiology of PPCSCI, and most of the research has been focused on eye movement testing. But we do know that vision therapy works, but we don't understand why. So the goal of this project is to understand, are there cerebrovascular changes following vision therapy in PPCSCI patients? We acquired concussed participants and had them complete a series of eye movement tasks in a virtual reality headset while collecting physiological data, including blood pressure, CO2, EKG, and mid-cerebral artery velocity, which is a blood vessel in the head. Following this, we took ultrasound imaging of the internal carotid artery in their neck, first in a seated position and then a supine position, which is laying down. We took the eye movement physiology data and split it according to each eye movement. Each one of these segments was analyzed and filtered in MATLAB. The ultrasound video, the video was put into a software called MAUI, and the diameter of the artery was tracked throughout the data collection. We used the audio to determine the velocity of the internal carotid artery blood using MATLAB as well. All of these were put together to give us our final physiological measures. So what we found is that following vision therapy in PPCSCI patients, males actually experienced a decrease in mean mid-cerebral artery velocity, while females experienced an increase. So this could point towards some kind of difference, a sex-based difference in the recovery timeline for males and females with PPCSCI. What we also found out is that mean carotid cerebral blood flow, which is the cerebral blood flow from the carotid artery originating in the neck, was actually increased following vision therapy in subjects in a seated position, but decreased in a supine position. So what do these results mean? Well, the initial data shows that there could be some kind of sex-based difference in mean mid-cerebral artery velocity following vision therapy. It could also indicate a difference in the recovery timeline between males and females, as previously stated. It also shows that there could be changes in carotid cerebral blood flow that are dependent on the posture of the PPCSCI patient. And we hope that through further data collection, we'll be able to better evaluate the physiology of PPCSCI patients following clinical recovery. I'd like to acknowledge my advisors, Dr. Ing Sanchez and Dr. Alvarez, as well as the Honor Summer Research Institute for funding this project. Thank you.
Okay, while the judges are still convening, let's take a 5 to 10 minute break, and I will corral you guys. Don't go far, but I'll corral you when the results are in. Okay? Thank you.
Okay. All right. Time to celebrate. So please take your seat and hold your breath. All right. So first of all of you, congratulations. You made me so proud of you, all of you. So I think that the board is very, very impressed, and we gave them the most difficult and most challenging task this year. So I just wanted to make sure that I express deep appreciation and pride in having you today and yesterday making your excellent, excellent presentation. So give yourself a big round of applause. Like any other competition, there are only a few winners, but you all are winners because the incredible experience that you had in presenting to the executive board, that is irreplaceable. That is invaluable. So you have earned that particular experience. You have learned something which is going to be an asset for you for the rest of your life. So again, I'm going to start with honorable mentions in each of the 5 categories. There is one honorable mention, and then we are going to announce the 3rd prize winner overall, and the 2nd prize winner overall, and the 1st prize winner overall. Everyone who participated will have the certificate of participation that you probably picked out from the desk. If not, then you can reach out to Susan Handy. And all of these honorable mentions and the winners will have additional certificate. That certificate is not ready yet. You can reach out to Sue, and then she will let you know when to pick it up. But we are going to provide you a trophy today. This trophy doesn't have your name, but it says 1st prize, 2nd prize, 3rd prize, and honorable mentions that you can take with you with pride, show your parents, show your family, and brag about a little bit. There's nothing wrong to brag about, right? You earned it. Okay, so this is how we're going to do when we provide the names to you. You're going to come forward. We're going to present it to you, and I'm going to request both of our co-chairs of the board, Brian and Govi, to join me on the podium. We'll take a picture, and then at the end, we want to take a group picture with the board members and all the winners. And after that, I will still be available. If you want to take additional pictures, we will do that, right? Okay, so let me start with the first group, which is bioscience and bioengineering. The honorable mention is Anushri Gupta. Evaluation of hydrogel scaffolds for myocardial regeneration. Come on. All right. Congratulations. Let them come, and then we'll have a picture. One of you come on the other side, right? Okay. And, all right. Congratulations. Well done.
Congratulations. Good job, man. Thank you.
Just stay here. Yeah, just stay here. The next honorable mention is in the category of data science and management, and the recipient is Kevin Diggs for soundly detecting memory leaks in the Linux kernel. All right. Yeah.
Yeah, you just hold it. Okay.
Yeah, hold it.
Yeah, there.
Yeah, right there.
Thank you very much.
Congratulations.
Thank you. Congrats, Kevin. Good job, man.
The next one in material science and engineering, and the recipient is honorable mention, Miriam Rahman, manufacturing a state-of-the-art selector valve for a miniature peptide synthesizer. Miriam? I guess she's not here, right? Okay. All right, let's move on. The next honorable mention in robotics and machine intelligence, Vignesh Netrapalli, improving captive data diversity via mood amplification for audio language tasks.
We don't have laser etch technology. We don't have the
Come on in the middle.
real-time names?
Yeah.
Not yet.
Congratulations.
Thank you. Thank you.
All right, congratulations.
Congrats, Vignesh.
And, okay. The last honorable mention is in the category environment and sustainability is Hana Shahinanian, Mercury Sketchers in Perth. Congratulations. Well done. Come on out. Yeah. Yes, hold it.
Looking right here. 1, 2, 3. Hold that. Thank you.
Thank you.
Thanks, Anna.
So now the overall excellence. And overall excellence, the first, second, and third. So we will start with third prize. Big congratulations and give a big hand to Rituja Bhattacharya. Trajectory clustering analysis for modeling human hand motion skills in robotics. You know, Robert Cohen would be very proud of you.
Excellent.
All right.
Thank you so much.
Show them this.
Yeah.
Yeah. Sure.
Better get a picture with that.
Okay.
There you go.
Yeah. All right. Congratulations. The second prize goes to Melissa Bilgili. Computational analysis for NB-stabilized isolated single metal atom catalyst. Yeah, it's heavy. All right, it's a little bit heavy. So come on. Congratulations. Come on. Yeah. It's a little. All right, congratulations.
Thanks,
Good
Anna.
job.
Congratulations.
All right. The big one. And drum roll. All right. So give it. Very proud. And actually, it was a consensus, no contest. Everybody loved the presentation. So the first prize, very proud of you, Stuti Mohan. Identifying novel concussion metrics through food trapping measurements. Stuti Mohan. She's not here? All right. Okay. Let me see. Biomedical engineering. Any faculty? I don't know who the advisor was. It's Chang, right? He's not here. Any faculty from biomedical engineering? Here? No?
Anybody at all?
Okay, yeah, come on in. All right. So pretend you are Stuti Mahan. And Dr. Lewis Hamilton, give him a big hand. He's a great, great supporter of the undergraduate research and summer program. And he runs the Honors College Summer Research Internship Program as well. Thank you so much.
She missed this too.
Yeah.
Should we give her our congratulations? I will. Thank you, brother.
All right, thank you. So again, that brings to the conclusion. Stay over here. So again, it has been wonderful and such a great pleasure listening to you and seeing you that how much dedication and passion and the commitment and the hard work you have put this summer. That makes me very, very assured that our future leadership is well placed among all of you, right? So take this opportunity, never shy away, take the leadership role into your hand and succeed. So I'm just going to ask the two of our co-chair to just give the closing remarks.
I'll nominate Brian to do the closing remarks, so go ahead.
All right.
Fantastic. Okay, go ahead. Do it.
Okay.
Why not me with this stuff? I just want to tell you, it's been an interesting 2 days. I fully agree with the scoring we just did and the awards we gave out. And I really hope you all enjoyed the process. You know, in some cases there were pins and needles, but that's normal. Just so long as you get used to doing it and standing up in front of people like this and just kind of ad-libbing whatever. And I only hope that you enjoy and you had a lot of fun doing whatever project you were doing. I don't need that. And and I wish you all a great remaining summer. I'm on my way out to Montana for a couple of weeks and to enjoy myself and join a bunch of friends and drink a lot of scotch.
Don't tell them that.
No, there is a reason to tell them that.
Oh, okay.
So that they get enough ambition to make some seriously good money so you can afford the scotch. So anyway, again, I wish you all a good summer, and thank you for your efforts and your time spent on doing this stuff, and I hope you enjoyed it.
All right, thank you.
Thanks, Brian. Thank you. All right, well, thank you. Nobody can follow that act, right? Thanks to each and every one of you. Thanks, Brian. By the way, very impressive presentations, highly inspiring. Thanks to each and every one of you. And I also want to thank Atam for pulling all this together. I think this is phenomenal. Year over year over year, we've seen the scope and the increase. So a big round of applause for Atam, Kimberly, and the whole team. Thank you.
All right. Enjoy the day.
Have a great evening.
And the weekend and the rest of the summer. See you back. Oh, all the winners who are here, could you come on the podium so that we can have the group photo? We always put it on the website. Yeah, all the board members and all the winners. Don't go away. The winners, please.